What if the act of observing something could change what is real? This is not science fiction, it is a question at the heart of modern physics. In the strange world of quantum mechanics, particles can exist in multiple states at once, like being in two places simultaneously. But when we observe them, that strange ambiguity disappears. They seem to choose a definite state. Why does this happen? And more importantly, what exactly counts as an observation? Some physicists have taken this mystery one step further. They have asked whether consciousness, our awareness, might play an active role in shaping reality. Is it possible that the mind of the observer collapses the quantum wave function? Does human consciousness, in some fundamental way, participate in the unfolding of the physical universe? In the early decades of the 20th century, physics underwent a quiet revolution, one that would eventually challenge the very meaning of reality. The certainties of classical physics, built over centuries since Isaac Newton, began to erode. Something strange was happening at the smallest scales of nature. Electrons, photons, and other subatomic particles refused to behave in predictable ways. They defied the neat laws that governed the motion of planets, the mechanics of levers, and the flow of electricity. Physicists were puzzled. Their instruments returned results that no one could easily explain. Light, for example, was behaving like both a wave and a particle. Electrons seemed to exist in multiple states at once, until someone measured them. The world of the very small did not follow the intuitive rules of the world we could see. At this crossroads, a new theory emerged: quantum mechanics. Quantum mechanics did not just describe odd behavior, it predicted it with astonishing accuracy. But it came with a catch. In this new framework, the act of measurement itself seemed to play a mysterious role. When you measured a system, it would suddenly collapse from a cloud of possibilities into a single, definite outcome. Before the measurement, the system was described by a wave function, an abstract mathematical expression of probabilities. After the measurement, the wave function resolved into a single state. But why? What caused this shift? This became known as the measurement problem, and it lay at the heart of quantum theory. The question was not simply about instruments or data collection. It was about the nature of observation. What does it mean to observe something? And more provocatively, could the conscious observer be playing an active role in this process? It was a daring idea that consciousness might influence physical reality, and it was not born from mysticism, but from genuine scientific confusion. The mathematics of quantum mechanics worked. It predicted outcomes with remarkable precision, but its interpretation, what the equations meant about the world, remained unsettled. The pioneers of quantum theory were well aware of this dilemma. Niels Bohr, working in Copenhagen in the 1920s, argued that quantum systems did not have definite properties until they were measured. This was not because they were hidden or unknown, but because the properties simply did not exist in a definite form until observation occurred. According to Bohr's view, known as the Copenhagen interpretation, reality at the quantum level was fundamentally probabilistic and incomplete without measurement. This stance was unsettling to many, especially Albert Einstein. Einstein believed in a fully real, objective world that existed independently of human observation. In his famous words, "I like to think the moon is there even if I am not looking at it." He saw quantum theory as a useful tool, but an incomplete one that would eventually be replaced by a deeper deterministic theory. The debate between Einstein and Bohr became one of the most famous philosophical confrontations in science. At the Solvay conferences in the late 1920s and early 1930s, the two giants engaged in intense discussions about the nature of reality. Bohr defended the view that the observer played a fundamental role, while Einstein insisted that the theory must be missing something. He even proposed thought experiments to show that quantum theory led to contradictions. Bohr, in turn, replied with arguments that emphasized the inseparability of the observer and the observed. Meanwhile, the younger generation of physicists, including Werner Heisenberg, Max Born, and Wolfgang Pauli, were developing the mathematics of quantum theory further. Heisenberg's uncertainty principle, proposed in 1927, showed that certain pairs of physical properties, like position and momentum, could not be precisely known at the same time. This was not a limitation of technology, but a fundamental feature of nature itself. Once again, the observer seemed to matter. As the 20th century progressed, quantum mechanics continued to deliver practical results. It explained the behavior of atoms, the structure of chemical bonds, and the workings of semiconductors. It led to the development of lasers, transistors, and even the foundations of modern computing. In field after field, quantum theory proved itself indispensable. But the mystery of observation remained unresolved. This mystery is sometimes framed in a simple yet profound question. Does the moon exist if no one is looking at it? Replace the moon with an electron and the question becomes central to quantum mechanics. Is the particle's position a definite fact before someone measures it? Or does the act of measurement bring the fact into being? At the heart of this lies the question of consciousness. Some interpretations suggest that it is not enough for a measuring device to interact with a quantum system. Rather, a conscious observer must become aware of the result. Only then, according to this view, does the wave function collapse and reality take a definite form. This idea, often associated with physicists like John von Neumann and later Eugene Wigner, has sparked decades of debate. It suggests that mind and matter are deeply intertwined in ways that physics does not yet fully understand. But not all physicists accept this. Many argue that invoking consciousness is unnecessary, that the process of measurement can be explained without resorting to the mind of the observer. Even so, the question persists. It is not about whether quantum mechanics works. It clearly does. The question is, what does it mean? What does the theory say about reality? And what role, if any, does human awareness play in shaping it? This is not just a question for philosophers. It is a question that reaches into the very foundations of science. If consciousness affects quantum outcomes, then our understanding of physics, biology, and even cosmology may need to be re-examined. If it does not, then we are still left with the puzzle of how observation collapses possibilities into actual events. Today, nearly a century after the birth of quantum mechanics, the question remains open. New experiments, new theories, and new interpretations continue to emerge. Some researchers explore quantum information theory and decoherence as solutions to the measurement problem. Others revisit old ideas about hidden variables or propose radical alternatives like the many worlds interpretation. Still others continue to ask whether consciousness itself might hold the key. Whatever the answer, the journey reveals something profound about the nature of science. Science is not just about collecting data, it is about understanding the principles that govern the world. When those principles challenge our assumptions about reality, objectivity, or the mind, we are faced with deep and difficult questions. At the dawn of the 20th century, physics was seen as nearly complete. Many scientists believed that the major forces of nature had been understood. Newtonian mechanics described motion, Maxwell's equations unified electricity and magnetism, and thermodynamics governed energy. It seemed that all that remained were a few details to be filled in, but those details would soon unravel everything. One of the first cracks appeared in the late 1800s with the problem of blackbody radiation. When scientists measured the spectrum of light emitted by heated objects, classical physics predicted that intensity would rise without bound at shorter wavelengths, a result known as the ultraviolet catastrophe. But this infinite energy made no sense. It was not just a mathematical error, it contradicted physical reality. In the year 1900, a German physicist named Max Planck proposed a daring solution. He suggested that energy was not continuous but came in discrete packets, which he called quanta. According to Planck, the energy of light was proportional to its frequency, multiplied by a constant, now called Planck's constant. With this assumption, he was able to match experimental results exactly. Though Planck initially viewed this as a mathematical trick, it laid the groundwork for quantum theory. Then, in 1905, a young patent clerk named Albert Einstein took Planck's idea one step further. Einstein proposed that light itself was made of particles, later called photons. In explaining the photoelectric effect, he showed that when light of a certain frequency shines on a metal surface, it can eject electrons, but only if the light's frequency exceeds a certain threshold. Classical wave theory could not explain this. Only by treating light as a stream of particles could the observations be understood. Einstein's idea was radical. It challenged the wave theory of light, which had been firmly established by experiments like Thomas Young's double-slit demonstration nearly a century earlier. But Einstein's predictions matched reality. In 1921, he was awarded the Nobel Prize, not for relativity, but for this explanation of the photoelectric effect. Over the next 2 decades, the puzzle deepened. In 1913, Niels Bohr introduced a model of the atom in which electrons orbited the nucleus in fixed energy levels. When an electron jumped between levels, it emitted or absorbed a photon of a specific frequency. Bohr's model explained the spectral lines of hydrogen, but it relied on rules that had no basis in classical physics. A few years later, in 1924, French physicist Louis de Broglie proposed an even more surprising idea. If light could behave like particles, perhaps particles like electrons could behave like waves. He introduced the concept of matter waves, suggesting that every particle had an associated wavelength. This wave-particle duality was confirmed experimentally when electron diffraction patterns were observed in 1927 by Clinton Davison and Lester Germer at Bell Labs. Meanwhile, a new mathematical framework was emerging. In 1925, Werner Heisenberg developed matrix mechanics, a way of calculating quantum properties without referring to the path of particles. Around the same time, Erwin Schrödinger formulated wave mechanics, using a differential equation that described how quantum systems evolve over time. The Schrödinger equation treated particles not as objects with definite trajectories, but as wave functions, mathematical functions that describe the probabilities of different outcomes. These two approaches, matrix mechanics and wave mechanics, were soon shown to be mathematically equivalent. Together, they formed the foundation of quantum mechanics. Unlike classical physics, which described objects with precise positions and velocities, quantum mechanics described systems in terms of probabilities. A particle could be in a superposition of states, existing in multiple possible configurations simultaneously, until measured. This probabilistic nature was not just a reflection of ignorance, it was a fundamental feature of the theory. Max Born, in 1926, clarified that the square of a particle's wave function represented the probability of finding it in a given location. This interpretation became central to the way quantum mechanics was understood. As quantum mechanics matured, it produced remarkable results. It explained the stability of atoms, the periodic table, and chemical bonding. It predicted the behavior of electrons in solids, enabling the development of semiconductors and eventually computers. Quantum mechanics was not just a theory, it became the basis for modern technology. But the more successful it became, the more its implications troubled physicists. The theory worked, but what did it mean? One of the first to raise concerns was Einstein. In a letter to Max Born in the 1920s, Einstein famously wrote, "I am convinced that God does not play dice." He could not accept that the universe was governed by pure chance. He believed that quantum mechanics, while accurate, was incomplete, that there must be underlying variables determining the outcomes we observe. Niels Bohr, on the other hand, accepted the probabilistic nature of the theory. He argued that the questions being asked about definite properties of particles before measurement simply did not make sense. In Bohr's view, quantum mechanics did not describe an objective reality independent of measurement. Instead, it described the outcomes of experiments. Reality, at the quantum level, was not something we could speak of without including the act of observation. This divide between those who believed quantum mechanics described a complete but probabilistic reality and those who thought it was incomplete would persist for decades. It set the stage for the famous Einstein-Bohr debates and the development of competing interpretations of the theory. At the center of all this was a new view of nature. In classical physics, objects had definite positions and velocities, regardless of whether anyone was observing them. In quantum mechanics, the observer seemed to play a more central role. Measurement was not just a way of finding out what was already there, it appeared to be part of what brought outcomes into being. This was not a conclusion anyone had expected. It emerged from the mathematics, the experiments, and the strange behavior of particles at the quantum scale. Physicists did not set out to link consciousness with physics. But the theory they built seemed to blur the line between subject and object, between the observer and the observed. Among all the strange demonstrations in quantum mechanics, one stands out as both profoundly simple and endlessly perplexing: the double-slit experiment. It is an experiment so basic that it can be explained in a few sentences, yet it reveals something deeply counterintuitive about the nature of reality. More than a century after it was first performed, it remains central to our understanding of how particles behave and how observation itself might play a critical role in shaping outcomes. The origins of the double-slit experiment date back to the early 19th century, long before quantum mechanics existed. In the year 1801, English polymath Thomas Young set out to test the nature of light. At the time, there was an ongoing debate: was light made of particles, as Isaac Newton had claimed, or was it a wave, as some newer theories suggested? To resolve this, Young devised a simple experiment. He shone light through two narrow slits cut into an opaque screen and projected the resulting pattern onto a surface behind it. If light were made of particles, one would expect to see two bright spots, each corresponding to a slit. Instead, Young observed a series of alternating light and dark bands, a pattern known as an interference pattern. This was a hallmark of wave behavior. It occurred because waves emerging from each slit overlapped and either reinforced or cancelled each other depending on their alignment. The conclusion was clear: light behaved like a wave. For over a century, this understanding went unchallenged. But with the birth of quantum mechanics in the early 20th century, the experiment gained new significance. As it became apparent that particles like electrons and even atoms could exhibit wave-like behavior, physicists began performing similar experiments with these particles, one at a time. When electrons were fired individually through the same type of double-slit apparatus, something astonishing happened. Even though the electrons were sent through one by one, the interference patterns still emerged, given enough time. It was as though each electron somehow passed through both slits simultaneously and interfered with itself. But electrons are particles, not continuous waves. They are detected as localized impacts on a screen, so how could they interfere with themselves? This implied that the electron did not take a single, well-defined path through one slit or the other. Instead, until it was observed or measured, it existed in a superposition of possibilities, passing through both slits at once and all paths in between. The situation became even stranger when physicists attempted to measure which slit the electron actually passed through. To do this, they placed a detector at each slit, designed to observe the electron's path. Once the measurement was made, the interference pattern vanished. Instead of the wave-like pattern, the result was two bands, as if the electrons had chosen a single slit and behaved like classical particles. This result seemed to hinge on the presence of measurement. When no one was looking, at least in the sense of making a measurement, the electron behaved like a wave. When its path was observed, it behaved like a particle. Observation appeared to change the outcome. But what does observation really mean in this context? The word can be misleading. In the scientific sense, it does not imply conscious awareness. It simply means that some form of measurement was made. Some interaction occurred that allowed information about the system to be recorded. Yet, the implications of the experiment led many to ask: is it possible that consciousness plays a role in collapsing the wave function? Could the awareness of the observer influence the result? This question did not come from popular science writers. It was debated among the very founders of quantum theory. In the early decades of the 20th century, thinkers such as John von Neumann and later Eugene Wigner explored the idea that consciousness might play a fundamental role in measurement. Although their views were not universally accepted, they reflected the sense of mystery surrounding quantum phenomena. Returning to the experiment itself, it is important to understand that the interference pattern forms over time. Each electron, or photon, or atom arrives as a tiny dot on the detection screen, but as more and more dots accumulate, the pattern begins to emerge. The wave function predicts the statistical distribution of those dots, but not the individual locations of each one. This probabilistic nature is built into the fabric of quantum mechanics. To test the limits of the observer effect, physicists have created variations of the double-slit experiment. One of the most famous is the delayed choice experiment, first proposed by American physicist John Archibald Wheeler in the 1970s. In this version, the choice of whether to observe the particle's path is made after it has passed through the slits, but before it hits the detection screen. Remarkably, the outcome still seems to depend on whether the measurement was made. It is as if the particle decides how to behave retroactively after the fact. Such experiments challenge our notions of time and causality. They suggest that the quantum world does not behave like a clockwork mechanism unfolding in a predictable sequence. Instead, outcomes depend on conditions set by the entire experimental setup, including future events that have not yet occurred at the moment of particle passage. Another modern twist is the quantum eraser experiment, which goes even further. In this version, information about the particle's path is recorded but then erased before detection. When the path information is erased, the interference pattern returns. When the information is preserved, the pattern disappears. These results are not just theoretical, they have been demonstrated in laboratories using photons and beam splitters, entangled particles, and clever timing arrangements. Once again, the experiments suggest that the availability of information, not just physical interactions, determines whether quantum behavior is wave-like or particle-like. But does this mean that a conscious observer is required? Most physicists would say no. The standard view is that measurement, in the quantum sense, is any irreversible interaction that leaves a trace in the environment. Consciousness may not be necessary. Still, the language we use, observation, measurement, collapse, can blur the lines. For laypeople, and even for some scientists, the boundary between physical interaction and awareness can become ambiguous. This is part of why the double-slit experiment has become such a touchstone in discussions about quantum theory and consciousness. Importantly, this experiment also introduces the concept of complementarity, championed by Niels Bohr. Complementarity holds that certain properties, like particle and wave behavior, are mutually exclusive, yet both are necessary to fully describe a quantum system. Which aspect you observe depends on how you set up the experiment. The choice of measurement context determines the outcome. This is not due to limitations of knowledge, but to the structure of nature itself. By the time of the mid-20th century, the double-slit experiment had become a foundational example in physics textbooks. It was no longer just a demonstration of wave interference. It had become a symbol of the central paradox of quantum mechanics, the coexistence of possibility and actuality, and the curious role of measurement in determining which is which. The experiment also underscores the non-classical logic of quantum systems. In classical physics, particles have definite paths. In quantum physics, paths are not real in the traditional sense until measurement defines them. In this framework, reality itself seems to depend on what is observed and how it is observed. As the framework of quantum mechanics began to take shape in the early decades of the 20th century, one of the most surprising discoveries was that nature itself seemed to resist being fully known. This was not merely a problem of limited technology or imperfect instruments. It was a fundamental limit built into the structure of the universe. That idea was crystallized in a principle proposed by the German physicist Werner Heisenberg in the year 1927. It would come to be known as the uncertainty principle, and it would change our understanding of measurement, observation, and the nature of physical reality. Werner Heisenberg was one of the leading figures in the early development of quantum mechanics. In his early 20s, he had already made significant contributions to atomic theory, and by the mid-1920s, he was working alongside other pioneers, such as Niels Bohr and Wolfgang Pauli. Heisenberg was deeply interested in the mathematical structure of quantum theory and how it could describe the behavior of atomic particles without relying on classical ideas of motion and trajectory. In classical mechanics, it is possible to describe the position and momentum of a particle with perfect precision. If one knows both where a particle is and how fast it is moving, one can, in principle, predict its future position and velocity with complete accuracy. This is the essence of determinism in Newtonian physics. But quantum mechanics challenged that certainty. Heisenberg's insight was that there are fundamental limits to what can be known about a quantum system. Specifically, he showed that certain pairs of properties, such as position and momentum, cannot both be known exactly at the same time. The more precisely one measures the position of a particle, the less precisely its momentum can be known, and vice versa. This is not a flaw in measurement technique, it is an inherent feature of the quantum world. The uncertainty principle is often misunderstood as a statement about disturbance. Some assume that measuring one quantity disturbs the system and thereby affects the other quantity, but this is not quite accurate. The principle is not about the act of measurement interfering with the system, it is about the mathematical structure of the wave function that describes the particle. In quantum mechanics, a particle is represented not by a point, but by a probability wave. The spread of this wave determines how precisely different properties can be defined. A wave that is sharply peaked in position must be spread out in momentum, and vice versa. Mathematically, the uncertainty principle can be expressed as an inequality involving Planck's constant, a fundamental number in quantum theory, but its implications are much more than mathematical. The principle tells us that the universe is not fully knowable in the classical sense. There is a limit to precision that is woven into the fabric of reality. This realization had profound consequences. It meant that the deterministic worldview of classical physics could no longer be sustained. Even with complete knowledge of a system's current state, the future was not perfectly predictable. The uncertainty principle was not a matter of ignorance. It was a statement about the way the world actually works. Heisenberg himself was aware of the philosophical weight of this discovery. He wrote that the observer could no longer be separated from the observed. In trying to describe a quantum system, one inevitably became part of the system. The sharp division between subject and object, so central to classical science, began to blur. This view fit well with the emerging Copenhagen interpretation, championed by Niels Bohr. According to this interpretation, the act of measurement is not a passive process of reading values. It is an active process that defines the properties being measured. Before measurement, a particle does not have a definite position or momentum. These properties are not hidden. They simply do not exist in a definite form until measured. The uncertainty principle supported this idea. It provided a formal basis for the claim that quantum properties are not just unknown prior to observation, they are undefined. Measurement does not merely reveal reality, it helps create it. The scientific community responded to Heisenberg's principle with both admiration and unease. Many physicists embraced it as a breakthrough that clarified the rules of the quantum world. Others, including Albert Einstein, viewed it with skepticism. Einstein continued to believe that quantum mechanics was incomplete. He suspected that there must be hidden variables, unknown factors that, if discovered, would restore determinism and allow precise predictions. In response to such concerns, Heisenberg and Bohr defended the principle not just as a practical rule, but as a statement about the limits of physical meaning. They argued that questions about unmeasured properties were meaningless within the quantum framework. To ask about a particle's exact position and momentum simultaneously was to ask a question that nature does not allow. The uncertainty principle also raised important questions about causality. If the future cannot be predicted with certainty, then cause and effect become probabilistic. Events unfold according to likelihoods, not certainties. This does not mean that the universe is chaotic or random in the everyday sense. Quantum mechanics provides extremely precise probabilities, and the results of repeated experiments match those predictions with remarkable accuracy. But it does mean that at the most fundamental level, nature includes an element of indeterminacy. Beyond its conceptual significance, the uncertainty principle has practical implications. It sets limits on what can be achieved in measurement and technology. For example, in the field of microscopy, there is a fundamental limit to how precisely particles can be imaged. In electronics, quantum uncertainty influences the behavior of semiconductors and the design of transistors. In quantum computing, the manipulation of qubits, quantum bits, must account for the uncertainties involved in measurement and interaction. Later developments in quantum theory, such as the concept of quantum entanglement, would challenge and expand the meaning of uncertainty. But Heisenberg's principle remains a cornerstone. It is one of the first indications that the rules of the quantum world are not just different from classical rules. They require a new way of thinking about knowledge, measurement, and reality itself. The uncertainty principle also laid the groundwork for deeper inquiries into the role of the observer. If measurement affects the properties of a system, then who or what constitutes an observer? Is it any interaction with the environment? Is it a conscious mind? Or is it simply the process of recording a result in a definite form? These questions would take center stage in the years that followed. Physicists and philosophers alike began to explore the implications of quantum theory, not only for physics, but for epistemology, the study of knowledge itself. They debated whether reality is objective or observer-dependent, and whether consciousness plays a role in defining the outcomes of measurements. By the late 1920s, the essential mathematical framework of quantum mechanics had been developed. Schrödinger's wave equation, Heisenberg's uncertainty principle, and the probabilistic interpretation advanced by Max Born were all in place. Experiments confirmed the predictions of the theory with growing precision, but one major question remained unresolved. What did all of this actually mean? To answer this, physicists turned to the task of interpreting quantum mechanics, not just as a tool for calculation, but as a way of understanding the nature of reality. Out of this effort emerged the most influential and widely taught interpretation of the theory, the Copenhagen interpretation. Named after the city where Niels Bohr worked and taught, this interpretation became the standard view of quantum mechanics for much of the 20th century. But it also sparked decades of debate, controversy, and confusion. The Copenhagen interpretation was not a formal doctrine laid out in a single paper. Rather, it was a shared understanding developed primarily by Niels Bohr and Werner Heisenberg, with contributions from others in the Copenhagen School of Physics. It sought to answer one of the most pressing questions in quantum mechanics: how and why does the wave function collapse during a measurement? In the Copenhagen view, quantum systems are described by a wave function which contains all possible information about the system's state. This wave function evolves deterministically according to the Schrödinger equation as long as no measurement is made. But when a measurement occurs, the wave function appears to collapse into a single, definite state. The Copenhagen interpretation does not explain this collapse as a physical process. Instead, it treats the wave function as a tool for calculating probabilities of different outcomes. The act of measurement simply reveals one of these outcomes and renders the rest irrelevant. This perspective is inherently epistemic. It focuses on what can be known about a system rather than assuming that physical properties exist independently of observation. According to Bohr, it is meaningless to speak of the position or momentum of a particle before a measurement. These properties do not exist in any definite way until they are observed. Bohr emphasized what he called complementarity, the idea that quantum entities can display seemingly contradictory behaviors depending on the experimental setup. For example, particles can behave like waves in one experiment and like particles in another. Both descriptions are necessary, but they cannot be used simultaneously. The nature of quantum systems depends on how they are interrogated by observers. Heisenberg echoed this idea, noting that the properties of a system do not exist independently of the measurement context. The observer and the observed cannot be separated in the way that classical physics assumes. Measurement is not a passive act of discovery, it is an active process that defines the properties being measured. The Copenhagen interpretation was, in part, a philosophical response to the conceptual problems of quantum theory. Bohr, in particular, was deeply concerned with the language used in science. He insisted that experimental results must be described in classical terms, lengths, times, voltages, even though the systems being studied did not obey classical laws. This insistence reflected a broader commitment to clarity and objectivity. Quantum mechanics, Bohr believed, must be understood not as a theory of things in themselves, but as a theory of the knowledge we can obtain through interaction with the world. This approach offered a way to sidestep the more troubling questions raised by quantum mechanics. It allowed physicists to work with the theory without having to explain what really happens when a measurement takes place. As physicist David Mermin would later summarize it, "Shut up and calculate." In this spirit, the Copenhagen interpretation provided a pragmatic way forward. It was grounded in the mathematics and supported by experiment. For many physicists, it was enough. Yet not everyone was satisfied. Albert Einstein, for one, strongly resisted the epistemic approach of the Copenhagen school. He believed that physics should describe an objective reality, not just the outcomes of measurements. He famously quipped that he could not believe the moon ceases to exist when no one is looking at it. For Einstein, the idea that properties like position or momentum do not exist until measured was deeply unsettling. Einstein's objections culminated in the development of the EPR paradox, named after Einstein, Podolsky, and Rosen, which sought to show that quantum mechanics was incomplete. But even before that, Einstein had raised questions at the Solvay conferences, where he and Bohr engaged in legendary debates about the meaning of quantum mechanics. At one point, Einstein proposed a thought experiment involving a particle passing through a slit and striking a screen. He asked whether it was possible to determine which slit the particle went through without destroying the interference pattern. Bohr replied by pointing out that such knowledge would necessarily disturb the system and eliminate the interference. For Bohr, this was not a flaw in the theory, it was an essential feature of quantum mechanics. Another challenge to the Copenhagen interpretation came from Erwin Schrödinger. In response to the idea of wavefunction collapse, Schrödinger proposed his now famous thought experiment involving a cat in a sealed box. The cat's fate, alive or dead, was linked to a quantum event, such as the decay of a radioactive atom. According to quantum mechanics, until the box is opened, the system is in a superposition of both alive and dead states. This, Schrödinger argued, was absurd. He intended the example as a critique of the Copenhagen interpretation, showing that its logic led to contradictions when applied to macroscopic objects. Despite these criticisms, the Copenhagen interpretation remained dominant through much of the 20th century. Part of its appeal lay in its consistency with experimental results, part of it lay in its avoidance of metaphysical speculation, and part of it lay in the authority of its proponents. Bohr, Heisenberg and others were among the most respected physicists of their time. However, as more physicists and philosophers began to reflect on the foundational questions of quantum theory, the Copenhagen interpretation came under increased scrutiny. Critics argued that it avoided rather than solved the measurement problem. It offered no clear account of what constitutes a measurement, or why measurement should cause a sudden collapse of the wave function, and it left open the question of whether consciousness plays any role in this process. Indeed, while the Copenhagen interpretation emphasizes the observer, it does not require that the observer be conscious. Measurement in this framework is defined as any interaction that yields a definite outcome, such as a detector clicking or a pointer moving. But the ambiguity surrounding the definition of measurement opened the door for other interpretations that did, in fact, invoke consciousness more explicitly. One such interpretation would later be advanced by Eugene Wigner, who argued that the wave function collapse does not occur until the result of a measurement enters consciousness. This idea, while controversial, grew in part from the conceptual foundation laid by the Copenhagen school. If properties do not exist until measured, and measurement involves an observer, then it is natural to ask whether the observer's mind is a necessary part of the process. By the early 1930s, quantum mechanics had established itself as one of the most successful theories in physics. Its predictions matched experimental results with astonishing accuracy, and it had already begun to reshape entire branches of science, from atomic chemistry to solid-state physics. Yet, despite its triumphs, the interpretation of the theory remained unsettled. What did it mean to say that a particle existed in a superposition of states? And what happened during the act of measurement that forced the system into a definite outcome? It was in this context that Austrian physicist Erwin Schrödinger introduced what would become one of the most famous thought experiments in the history of science. Known today as Schrödinger's cat, this imaginative scenario was not intended to clarify the Copenhagen interpretation, but to challenge it, to expose what Schrödinger saw as the conceptual absurdity of applying quantum principles to everyday objects. The idea, first published in a paper in the year 1935, begins with a simple setup. Imagine a sealed box. Inside the box is a cat, a small amount of radioactive material, a Geiger counter, a vial of poison gas, and a triggering mechanism. The arrangement is designed so that if a single atom of the radioactive material decays within a given time, say 1 hour, the Geiger counter detects it, activates the mechanism, and breaks the vial, releasing the poison and killing the cat. If no decay occurs, the cat remains alive. According to quantum mechanics, the radioactive atom exists in a superposition of decayed and not decayed states until it is measured. Because the entire system is linked, the atom, the detector, the mechanism, and the cat, this superposition extends to the whole box. As a result, the cat must be described as being in a superposition of alive and dead until someone opens the box and makes an observation. Schrödinger's goal was not to suggest that cats truly exist in such states. Quite the opposite. He believed that the logic of the Copenhagen interpretation led to absurd consequences when extended to macroscopic systems. In his own words, it was quite ridiculous to think of a cat as simultaneously alive and dead. The thought experiment was intended to show that the quantum description, while powerful, could not be complete or literally true in all cases. The paradox at the heart of Schrödinger's cat is not about the mechanics of decay or the reliability of detectors. It is about where the boundary lies between the quantum and classical worlds. At what point does a superposition collapse into a single reality? Does this happen when the Geiger counter clicks, when the poison is released, when the box is opened, or when a conscious observer becomes aware of the result? This ambiguity was already present in the Copenhagen interpretation, but Schrödinger's example made it impossible to ignore. It forced physicists to confront a crucial question. If measurement collapses the wave function, what counts as a measurement? Does it require an observer, a record, a human mind? Some responses attempted to sidestep the issue. According to one view, the collapse occurs when the system becomes entangled with a larger environment, what we now call decoherence. In this view, the interaction of the atom with the detector, and then with the cat, and then with the air molecules in the box, is enough to render the outcome effectively irreversible. The superposition still exists in theory, but for all practical purposes, the system behaves as if a definite outcome has occurred. However, this line of thinking had not yet been formalized in Schrödinger's time. His concern was with the literal meaning of the quantum formalism. If we take the mathematics seriously, then the cat really is in a mixed state until an observation is made. This, he argued, was a sign that something was missing from the theory, either in its formulation or in its interpretation. Schrödinger's cat also reignited debates about realism in physics. In classical terms, we assume that systems have definite properties, whether or not we observe them. A cat is either alive or dead, regardless of whether anyone is watching. But quantum mechanics, especially as interpreted through the Copenhagen lens, challenges that assumption. It suggests that reality is not fully determined until measured. This point was deeply unsettling to many physicists, including Albert Einstein. In the same year that Schrödinger published his cat paradox, Einstein, along with Boris Podolsky and Nathan Rosen, formulated what would become known as the EPR paradox, a different thought experiment designed to highlight the incompleteness of quantum mechanics. Though the two paradoxes addressed different issues, they shared a common motivation: to demonstrate that quantum theory, while powerful, could not be the full story. The cat paradox also inspired future developments in experimental physics. While no one has ever built a literal Schrödinger's cat box, researchers have created quantum systems that mimic its structure. For example, physicists have constructed quantum superposition states involving superconducting circuits, ions, and photons, systems large enough to be seen with the naked eye. These experiments aim to test the boundaries of quantum behavior in increasingly macroscopic contexts. In recent years, some experiments have even begun to approach the scale at which the transition from quantum to classical might be observed. In these experiments, researchers look for signs of decoherence, the process by which a quantum system loses its coherence and begins to behave classically due to interactions with its environment. While these studies have not resolved the measurement problem, they have added new dimensions to the discussion. They suggest that while superpositions are real, they are extremely fragile and difficult to preserve at large scales. Yet the core paradox remains. Even if decoherence explains the appearance of collapse, it does not explain why a single outcome is experienced rather than a mixture. From a purely mathematical standpoint, the wave function still contains multiple possibilities. But from a lived perspective, we observe only one. The cat is either alive or dead, not both. This distinction has led some physicists and philosophers to explore more radical interpretations. In one such view, all possible outcomes of a quantum measurement actually occur in separate branches of the universe. This is the many worlds interpretation, which we will explore in more depth later. But for now, it is important to note that Schrödinger's cat remains a central metaphor in quantum physics, precisely because it forces us to confront the limits of what the theory can explain. In educational settings, the cat paradox is often used to introduce students to the concept of superposition and the mysteries of quantum measurement. But beyond the classroom, it continues to provoke deep questions about the nature of reality. Is the world fundamentally indeterminate until observed, or is there an objective reality that exists independently of us, hidden behind the veil of quantum probabilities? Schrödinger's original intention was not to argue for one answer or another, but to show that the questions themselves are unavoidable. His cat was not a symbol of mystical ambiguity, it was a challenge to the coherence of the prevailing interpretation. And that challenge still stands. Throughout the early development of quantum mechanics, one voice stood out in persistent opposition to the dominant interpretation of the new theory. That voice belonged to Albert Einstein. Though he had been instrumental in the foundations of quantum theory, especially with his explanation of the photoelectric effect and his introduction of light quanta, Einstein became one of its most vocal critics. His concerns were not about the mathematical formalism of quantum mechanics, which he acknowledged as empirically successful, but about what the theory implied about the nature of reality. Einstein's central objection was philosophical and deeply rooted in his belief in an objective, observer-independent universe. He could not accept that reality depended on whether it was observed. In his view, the moon does not cease to exist when no one is looking at it, and particles must have definite properties, even if those properties are not being measured. For Einstein, a physical theory should describe what is, not just what can be observed. This conviction led him to challenge the Copenhagen interpretation and its implications. One of the earliest and most memorable exchanges on this front occurred during the series of Solvay conferences held in Brussels. These conferences brought together the leading physicists of the era, including Niels Bohr, Werner Heisenberg, Max Born, Paul Dirac, Wolfgang Pauli, and Einstein himself. The discussions were intense, and at times even theatrical. At the fifth Solvay conference in the year 1927, Einstein presented a series of thought experiments aimed at revealing the incompleteness or inconsistency of the Copenhagen view. In one such example, Einstein considered a particle passing through a slit and striking a screen, forming an interference pattern. He argued that, in principle, one could measure the recoil of the slit device itself to determine which path the particle took. If that were possible, then both the interference pattern and the path information could be known simultaneously, seemingly contradicting the uncertainty principle. Bohr responded with careful analysis, pointing out that any such measurement would disturb the system in a way that destroyed the interference pattern. He maintained that quantum mechanics was internally consistent, provided one accepted its rules. These exchanges, though respectful, revealed a fundamental divide between the two men. Bohr accepted complementarity and the limitations imposed by quantum theory. Einstein did not. Despite the heated debates, Einstein's concerns continued to evolve. By the mid-1930s, he began working with colleagues Boris Podolsky and Nathan Rosen to formulate a more formal challenge to quantum mechanics. Their work culminated in the paper titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?", published in the year 1935. This paper introduced what is now known as the EPR paradox. In the EPR paper, Einstein and his co-authors considered a pair of particles that interact and then separate in such a way that their properties become correlated. For instance, suppose two particles are prepared in a state where their total momentum is zero. If one particle is later measured to have a certain momentum, then the other must have an equal and opposite momentum. Similarly, if the position of one particle is measured, the position of the other can be inferred. This is true even if the particles are separated by great distances. Einstein, Podolsky, and Rosen argued that because one could predict the result of a measurement on the second particle without disturbing it directly, the second particle must have had a definite property all along. In other words, the outcome was not created by the act of measurement. Therefore, the quantum mechanical description, relying on superposition and uncertainty, must be incomplete. There must be hidden variables unknown to quantum theory that determine these outcomes. This argument was powerful because it did not rely on any particular measurement. It used only the assumptions of locality, that events in one region cannot instantly affect events in another faraway region, and realism, the belief that physical properties exist independently of observation. If these two assumptions held true, then quantum mechanics could not be a complete theory of nature. Bohr responded swiftly to the EPR paper, though his reply was characteristically dense and difficult to interpret. He rejected the premises of the EPR argument, particularly the notion that quantum mechanics should describe an objective reality independent of measurement. Bohr insisted that quantum descriptions are context-dependent and that the act of measurement is fundamental to defining physical quantities. The debate between Einstein and Bohr did not lead to a consensus. For the remainder of his life, Einstein continued to search for a deterministic alternative to quantum mechanics, something that would restore clarity and objectivity to physics. He explored unified field theories and other mathematical structures, but he never succeeded in formulating a complete alternative to quantum theory. Although Einstein's objections did not convince most of his contemporaries, they laid the groundwork for future investigations into the foundations of quantum mechanics. In particular, the EPR paradox introduced the concept of quantum entanglement, a phenomenon that would later become central to quantum information theory and experimental tests of the nature of reality. Quantum entanglement, as described in the EPR paper, refers to the deep correlation between particles that have interacted and then moved apart. These correlations appear to transcend distance, leading to what Einstein famously called spooky action at a distance. He believed such effects violated the principle of locality and hinted at some deeper hidden mechanism beneath quantum theory. At the time, these ideas were considered largely philosophical. There were no experiments capable of testing whether the predictions of quantum mechanics or the assumptions of local realism were correct. That would change in the second half of the 20th century, when physicist John Bell devised a theorem that allowed these competing ideas to be tested. But in Einstein's era, the debate remained unresolved. It is important to recognize that Einstein did not reject quantum mechanics out of stubbornness or nostalgia for classical physics. He understood the power of the theory and acknowledged its success in explaining observed phenomena. His objection was not to the mathematics, but to the interpretation. He sought a deeper, more complete account of reality, one that would not require abandoning determinism or locality. Einstein's critique resonates because it speaks to a broader tension in science, the desire for a coherent, intelligible picture of the world, even when experimental results challenge that coherence. His insistence on realism and his refusal to accept incompleteness for its own sake forced physicists to sharpen their thinking and clarify their assumptions. In the decades following the Einstein-Bohr debates, the strange features of quantum mechanics remained unresolved at a conceptual level. Most working physicists chose to ignore the foundational puzzles and focused instead on applying the theory to practical problems in atomic physics, chemistry, and solid-state systems. The mathematics of quantum mechanics worked extraordinarily well, and many came to accept Niels Bohr's position that the theory needed no deeper interpretation beyond its predictive success. Yet not everyone was satisfied with this pragmatic attitude. The tensions between quantum mechanics and Einstein's insistence on locality and realism continued to simmer in the background. The central dilemma posed by the EPR paradox, whether quantum mechanics was a complete theory or whether it needed hidden variables to restore determinism, remained a philosophical question. That is, until a breakthrough came in the early 1960s, when physicist John Stuart Bell found a way to test these competing ideas experimentally. John Bell was born in Belfast, Northern Ireland, in the year 1928. Trained as both a physicist and an engineer, he worked at the European Organization for Nuclear Research, better known as CERN, on accelerator physics. But Bell also harbored a deep interest in the philosophical underpinnings of quantum theory. Troubled by the unresolved questions raised by Einstein and others, Bell revisited the EPR paradox and asked whether it might be possible to settle the matter not through thought experiments, but through real-world data. What Bell discovered was astonishing. In the year 1964, he published a paper titled On the Einstein-Podolsky-Rosen Paradox. In it, he introduced what would later be called Bell's theorem, a mathematical result that demonstrated a crucial difference between the predictions of quantum mechanics and those of any theory based on local hidden variables. To understand Bell's insight, it is necessary to return to the notion of entanglement. When two particles interact and then move apart, quantum mechanics allows them to remain entangled, meaning their properties are correlated in such a way that measuring one particle immediately determines the outcome for the other, regardless of how far apart they are. In the EPR view, this implied that both particles must have carried hidden information from the start, real properties that existed before measurement, and did not require instantaneous action across space. Bell formalized this idea using what are now known as Bell inequalities. These inequalities place limits on the statistical correlations that can arise between two systems if those systems are governed by local hidden variables. In other words, Bell showed that if reality obeys the principles of locality, no faster than light influence, and realism, definite properties existing prior to measurement, then there is a maximum degree of correlation that can be observed between entangled particles. However, quantum mechanics predicts stronger correlations that violate Bell's inequalities. If such violations are observed in experiment, then at least one of the assumptions behind local hidden variable theories must be false. Either realism or locality, or both, must be abandoned. The implications of Bell's theorem are profound. It transforms what was previously a philosophical debate into an empirical question. For the first time, physicists had a way to test whether the universe behaves according to the assumptions of classical realism or according to the strange, non-local correlations predicted by quantum mechanics. Bell himself was cautious but deeply aware of the significance of his result. He wrote that the apparent conflict between quantum mechanics and local realism was not just a matter of interpretation, it was a matter of physics. As he put it, the EPR argument is untenable unless we can see our way to a complete theory in which the measurement results are determined by properties the systems carry before and independently of the measurement. Bell's theorem inspired a new generation of experimentalists to test the limits of quantum theory. In the 1970s and 80s, a series of pioneering experiments were carried out by physicists such as John Clauser, Stuart Friedman, and especially Alain Aspect, working at the Institut d'Optique in France. In these experiments, pairs of entangled photons were generated and sent in opposite directions toward detectors. The settings of the detectors, typically involving the orientation of polarizing filters, could be changed independently. The goal was to measure whether the correlations between the detection results violated Bell's inequalities. Aspect's experiments, conducted in the early 1980s, were among the first to show clear violations of Bell's inequalities under well-controlled conditions. The results matched the predictions of quantum mechanics and ruled out a wide class of local hidden variable theories. However, critics pointed out that these experiments had certain loopholes that left room for doubt. For example, one concern was the locality loophole, the possibility that information about one detector's setting could reach the other detector before the measurement was completed. Another concern was the detection loophole, the fact that not all entangled particles are detected, potentially biasing the sample. Over the following decades, these loopholes were gradually closed. In the 21st century, a new generation of experiments, sometimes called loophole-free Bell tests, employed advanced techniques in quantum optics and fast electronics to eliminate both the locality and detection loopholes. In particular, experiments conducted in the Netherlands in the year 2015 by a team led by Ronald Hansen at Delft University demonstrated violation of Bell's inequalities under conditions that satisfied strict separation of measurement events and high detection efficiency. The conclusion was unmistakable. Nature violates Bell's inequalities, just as quantum mechanics predicts. The correlations between entangled particles cannot be explained by any local hidden variable theory. Something deeper and more non-local is at work. What does this mean for the broader question of reality? The violation of Bell's inequalities forces physicists to confront the implications of quantum entanglement. Either the world is non-local in the sense that actions in one place can influence outcomes elsewhere instantaneously, or we must abandon the idea that particles possess definite properties before measurement. Some interpretations of quantum mechanics embrace non-locality, others abandon realism, still others attempt to reinterpret the meaning of probability and information. But no interpretation consistent with the data can preserve both locality and realism in the classical sense. Bell's theorem draws a clear line in the sand. It is important to understand that these results do not imply the possibility of faster-than-light communication. Quantum entanglement produces correlations, but it does not allow information to be transmitted in a controllable way. Nevertheless, the mere existence of these correlations across arbitrarily large distances challenges our classical intuitions about causality and separability. Bell's theorem does not mention consciousness. It does not rely on the presence of an observer in the usual sense. But by revealing the deep structure of quantum entanglement, it reignites the question of what it means to observe a quantum system. If outcomes are not determined until measurement, and if measurement creates correlations that defy classical explanation, then the act of observation, however defined, remains central to the story. For many physicists, the lesson of Bell's theorem is that reality is not composed of separate, independently existing parts. Instead, quantum systems form a web of correlations that resist classical decomposition. The boundaries between parts of a system, between the observed and the observer, are less clear than once thought. Bell's legacy is immense. His work reshaped the foundations of quantum theory and opened the door to quantum information science, including quantum computing, quantum cryptography, and quantum teleportation. But beyond technology, Bell's theorem challenges our understanding of the physical world and our place within it. In the classical worldview, the observer is a passive entity. Observation merely reveals the properties of an object that already exist, independent of whether anyone is looking. A thermometer reads the temperature, but it does not determine it. A telescope magnifies the light of distant stars, but it does not alter their course. The universe unfolds according to fixed laws, and the observer is simply an external witness. Quantum mechanics, however, forces us to reconsider this role. Since the earliest interpretations of the theory, the observer has been central, not because of any mystical property, but because of what the mathematics and experiments seem to imply. The very act of observation appears to play a role in determining which outcomes manifest and which remain only possibilities. But what does it mean to observe a quantum system? What qualifies as an observer? And must that observer be conscious? These questions are more than philosophical curiosities. They lie at the heart of the measurement problem, the unresolved puzzle of how and why a quantum system transitions from a superposition of multiple possible outcomes into a single, definite result. In the formalism of quantum mechanics, a system evolves smoothly and predictably according to the Schrödinger equation until a measurement occurs. At that moment, the wave function appears to collapse into a single state, but the theory itself does not specify exactly when, where, or how this collapse occurs, nor does it say what qualifies as a measurement. In the Copenhagen interpretation, the concept of measurement is treated as fundamental. Properties such as position, momentum, or spin do not have definite values until they are measured. However, this explanation avoids addressing what precisely constitutes a measurement. Is it simply any interaction with a physical system? Must the result be recorded? Does the process require a conscious mind to be aware of the outcome? This ambiguity has prompted various attempts to define the role of the observer more clearly. Some interpretations treat the observer as any macroscopic apparatus that interacts with the quantum system in a way that yields irreversible change. In this view, observation is not about human perception, but about physical processes, like a photon striking a detector and triggering a cascade of events that produce a readable signal. According to this approach, consciousness is not required. The observer could be a machine, a cloud of gas, or even another quantum system, provided the interaction leads to a classical, irreversible result. Others, however, have argued that such a definition is incomplete. In the mid-20th century, some physicists began to consider whether consciousness itself might be necessary to complete the measurement process. This idea was explored most notably by John von Neumann, a Hungarian-American mathematician and physicist whose contributions to quantum mechanics were both technical and conceptual. In the year 1932, von Neumann published The Mathematical Foundations of Quantum Mechanics, a work that formalized the measurement problem in rigorous terms. He showed that if the entire measurement chain, from the quantum particle to the detector to the measuring apparatus, is treated as part of a larger quantum system, then the problem of superposition simply moves up the chain. The detector becomes entangled with the particle, the apparatus becomes entangled with the detector, and so on. Nowhere in this chain does the wave function necessarily collapse. This leads to a striking conclusion. Unless a collapse is introduced at some stage by hand, the superposition persists. Von Neumann proposed that the only place where collapse might naturally occur is at the level of consciousness, the mind of the observer. In other words, it is only when a conscious entity becomes aware of the result that the quantum system resolves into a definite state. This idea, sometimes referred to as the von Neumann-Wigner interpretation or the consciousness causes collapse hypothesis, is not widely accepted among physicists. It introduces elements, specifically the mind, that lie outside the usual domain of physics. Yet it remains a topic of interest precisely because it confronts the measurement problem directly and seeks to identify a definite point where quantum indeterminacy ends and classical reality begins. The role of the observer also appears in the work of Eugene Wigner, another Hungarian-American physicist and Nobel laureate. Wigner extended von Neumann's ideas in a thought experiment known as Wigner's Friend, which we will explore in the next section. For now, it is important to note that Wigner explicitly argued for a role of consciousness in quantum mechanics, suggesting that the wave function collapse does not truly happen until a conscious observer registers the outcome. However, not all thinkers who place emphasis on the observer go so far as to invoke consciousness. Some prefer to see observation as a physical interaction that produces a record, a change in the system that could, in principle, be known. In this view, the observer is simply any subsystem capable of distinguishing between different possible outcomes. This perspective aligns more closely with modern developments in quantum information theory, where information plays a central role in defining the state of a system. Still, the question remains: what, precisely, transforms a quantum possibility into a classical fact? Is it the amplification of a quantum event to a macroscopic scale? Is it the formation of a stable record? Or is it the experience of awareness itself? One challenge in answering this question is that consciousness itself is not well understood. Neuroscience continues to investigate the biological basis of awareness, but no universally accepted theory of consciousness exists. To invoke consciousness in the context of quantum mechanics is therefore to rely on a concept that is already mysterious in its own right. This has led many physicists to avoid the idea altogether, preferring explanations that remain within the established framework of physics. Nevertheless, the role of the observer remains unavoidable in discussions of quantum mechanics. Even interpretations that seek to eliminate wave function collapse, such as the many worlds interpretation, must account for the appearance of definite outcomes. In these models, the observer splits into multiple versions, each experiencing a different result. The mystery is not eliminated, it is rephrased. The observer also features prominently in newer epistemic interpretations of quantum mechanics, such as QBism, which treats the wave function not as an objective feature of reality, but as a reflection of the observer's personal knowledge and expectations. In this view, quantum probabilities are subjective, and the observer plays a central role in constructing reality through belief and experience. We will examine QBism in greater detail in a later section. For now, it is enough to recognize that the observer, whether conscious or not, is deeply entangled, conceptually and physically, with the quantum world. Unlike in classical physics, where systems evolve independently of observation, quantum mechanics requires us to consider the process of observation as part of the system itself. The observer is no longer a detached spectator, but a participant in the unfolding of events. This shift has profound implications, not just for physics, but for how we understand knowledge, causality, and reality itself. It challenges the traditional boundaries between subject and object, between knower and known. Whether or not consciousness is required, the mere fact that observation seems to influence outcomes suggests that we must rethink what it means to measure, to observe, and to know. In the growing collection of quantum thought experiments, one stands out for how it sharpens the paradox surrounding the observer's role. The Wigner's friend scenario, conceived by physicist Eugene Wigner in the mid-20th century, this thought experiment extends the famous Schrödinger's cat paradox by introducing a second observer into the picture, someone who observes the observer. In doing so, it forces us to confront uncomfortable questions about the nature of reality, consciousness, and what it means for a measurement to occur. Eugene Wigner was not only a brilliant theoretical physicist, he also had a keen interest in the philosophical implications of quantum mechanics. A Nobel laureate for his work in the theory of symmetries in atomic nuclei, Wigner was deeply familiar with the mathematical formalism of quantum theory, but like John von Neumann before him, he was unsettled by the notion that the wave function, and thus physical reality itself, depends on the act of observation. Wigner took this further by asking, what happens when the observer becomes part of the system being observed? To illustrate his point, Wigner imagined the following scenario. Suppose a friend of Wigner, let's call this person simply the friend, is in a sealed laboratory performing a quantum measurement. Inside the lab, the friend measures the spin of a single particle, which has been prepared in a superposition of spin up and spin down. Upon measurement, the friend sees a definite outcome, either spin up or spin down. According to the standard rules of quantum mechanics, the act of measurement causes the wave function to collapse into one of the two possibilities. Now, from the perspective of the friend inside the laboratory, everything is settled. A result has been observed, recorded, and in principle could be shared with anyone else. But Wigner is outside the sealed lab and has no knowledge of the result. According to Wigner, the entire laboratory, including the friend and the measurement apparatus, should be treated as a single quantum system. From his point of view, until he opens the lab and interacts with his friend, the system remains in a superposition. That is, Wigner would describe the friend as being in a superposition of having observed spin-up and having observed spin-down. This leads to an extraordinary conclusion. According to quantum mechanics, the friend experiences a definite outcome, but for Wigner, the entire lab, including the friend, is still in a superposition. Both descriptions are valid within their respective reference frames. So which one reflects reality? The core paradox is this: can two observers assign different states to the same system, with both descriptions being correct according to quantum theory? If so, then reality may not be absolute. It may be observer-dependent. This possibility challenges our most basic intuitions about truth and facts. Is there an objective reality in which an event either happened or did not happen? Or are outcomes only real relative to the observer who experiences them? Wigner's thought experiment becomes even more tangled when extended further. Suppose that after performing the measurement, the friend sends Wigner a message confirming that a definite outcome was observed, without saying what the result was. Now Wigner knows that the friend saw something definite, but he still has not interacted with the system himself. According to quantum mechanics, does the wave function remain uncollapsed? And if it does, what exactly does it mean for someone to have observed a result while still being part of a superposition? Wigner's answer was radical. He argued that it is only when a conscious observer becomes aware of the measurement result that the wave function truly collapses. In this view, the friend sees a definite result, but from Wigner's standpoint, that experience is not yet part of objective reality. Only when Wigner himself becomes aware of the result does the system resolve into a definite state. Thus, consciousness, specifically the conscious awareness of an observer, is what completes the measurement process. This interpretation implies a hierarchy of observation. The collapse of the wave function depends on the conscious observer who is last in line. If the observer is embedded in the quantum system, as the friend is, their own awareness does not collapse the system for others. Only when an external conscious agent becomes aware of their result does the collapse occur universally. In effect, it is not just the act of observation that matters, it is whose observation counts. The Wigner's friend scenario has generated intense debate. Critics argue that it introduces unnecessary complications by appealing to consciousness, a concept that is difficult to define and not part of any physical theory. Others suggest that Wigner's framework violates the spirit of objectivity in science by making reality dependent on personal experience. In response to these concerns, alternative interpretations of quantum mechanics have been proposed. Some avoid the problem entirely by denying that wave function collapse ever happens. The many worlds interpretation, for example, holds that both possible outcomes of the friend's measurement occur, each in a separate branch of the universe. In this view, Wigner and his friend each occupy different branches with consistent histories. There is no contradiction because every possible result happens somewhere, and there is no need for collapse. Another approach is the relational interpretation of quantum mechanics. This interpretation suggests that quantum states are not absolute but are always relative to the observer. The friend's observation is valid within their frame of reference, while Wigner's description of the lab as a superposition is equally valid from his own standpoint. There is no contradiction because quantum states are not objective features of reality. They are descriptions of the information one system has about another. More recently, experimental proposals inspired by the Wigner's friend thought experiment have entered the realm of feasibility. In simplified versions using entangled photons and beam splitters, researchers have begun to explore whether it is possible to observe situations in which different observers register different realities. Though no experiment has yet fully replicated the scenario with human observers, the results suggest that the tension between observer perspectives is not merely philosophical, it may be testable. In 2019, a team of physicists published a study based on a variant of the Wigner's friend experiment. They used entangled photons to simulate a situation in which two friends perform measurements inside isolated labs, while two Wigners outside the labs make their own measurements. The results indicated that it may be impossible to assume a shared objective reality in which all observers agree on the outcome. If these findings are confirmed, they could imply that facts themselves are relative to the observer, at least in the quantum domain. This conclusion, while startling, resonates with some of the earliest insights in quantum mechanics. It reinforces the idea that the observer cannot be cleanly separated from the observed, and that knowledge is deeply tied to context. Whether or not consciousness is ultimately required for wave function collapse, the Wigner's friend scenario forces us to confront the limitations of a purely objective description of reality. Eugene Wigner later softened his position. In his later writings, he acknowledged that appealing to consciousness might not be necessary, and that the measurement problem might be resolved through better understanding of physical processes like decoherence. Nevertheless, the thought experiment that bears his name remains one of the most vivid illustrations of quantum theory's conceptual challenges. At its core, the Wigner's friend paradox does not merely complicate the question of measurement, it reframes it. It shows that our conventional ideas of a single, shared reality may not hold up under quantum scrutiny. It asks us to consider whether different observers might inhabit different versions of reality and what that means for the nature of truth, observation, and experience. At the heart of quantum mechanics lies a puzzle that has resisted resolution since the earliest days of the theory. This puzzle is not about mathematics, nor about the success of quantum predictions, which are among the most accurate in all of science. Rather, it concerns what the theory actually says about the world. This is known as the measurement problem, and it remains one of the deepest and most debated issues in the foundations of physics. To understand the measurement problem, we must begin with the basic rules of quantum mechanics. When a quantum system evolves in time, it does so according to a mathematical equation called the Schrödinger equation. This equation is deterministic, continuous, and fully governed by the initial state of the system. If no measurement is made, the system's wave function, a mathematical object that encodes all possible outcomes, evolves smoothly and predictably. However, when a measurement is performed, something very different seems to happen. Instead of continuing its smooth evolution, the wave function collapses into a single outcome. For example, if a quantum particle is in a superposition of being in multiple positions, then upon measurement, it appears in one specific location and the other possibilities disappear. This process is abrupt, non-deterministic, and not described by the Schrödinger equation. Thus, quantum mechanics has two seemingly incompatible rules. One for the evolution of systems when they are not being observed, and another for what happens during a measurement. But the theory does not clearly define when or how the transition between these two rules takes place. It does not say precisely what constitutes a measurement or why measurement should cause collapse. This is the measurement problem. How can a theory that governs the entire universe require a special, undefined process, measurement, that is outside the formalism of the theory itself? And what exactly causes the wave function to collapse? Early quantum theorists were aware of this dilemma. Niels Bohr sidestepped the problem by arguing that the act of measurement must be described using classical terms. For Bohr, quantum systems could only be understood through their interaction with classical apparatuses, and the cut between quantum and classical was a practical necessity. He maintained that quantum mechanics did not describe the world as it is, but only what we can say about it. But this approach left many questions unanswered. What counts as a classical system? Where does the boundary lie between the quantum and classical domains? And what determines when collapse occurs? John von Neumann was one of the first to treat this issue with mathematical rigor. As discussed in a previous section, von Neumann showed that if both the measuring apparatus and the system being measured are treated quantum mechanically, then the whole system becomes entangled. No definite outcome appears unless an external process, something beyond the physical description, collapses the wave function. Von Neumann's proposal was that this process might involve the consciousness of the observer. This was a bold suggestion, and it opened the door to interpretations that assigned a special role to the mind in resolving quantum ambiguity. Others, however, rejected this move. They argued that consciousness should not be brought into physics unless absolutely necessary. Instead, they sought physical mechanisms that might explain the appearance of collapse without invoking the observer's mind. One such proposal is known as decoherence. Developed more fully in the latter half of the 20th century, decoherence theory attempts to explain why quantum systems appear to collapse when measured. According to this idea, when a quantum system interacts with its environment, the superposition of states becomes entangled with countless degrees of freedom, such as air molecules, photons, or the atoms of a measuring device. This entanglement spreads the quantum information so widely and irreversibly that the original superposition becomes effectively lost. From the perspective of the system, it appears as if one outcome has been selected, even though the wave function itself has not truly collapsed. Decoherence provides a way to understand why quantum behavior is not seen at macroscopic scales and why classical reality appears stable. However, decoherence does not solve the measurement problem entirely. It explains how quantum systems become entangled with the environment and why interference between different outcomes is suppressed, but it does not explain why a single outcome is observed. The formalism still contains all possible outcomes, and it does not specify which one becomes real. Decoherence explains why we do not see superpositions, but not how a particular result is chosen. This distinction is critical. Decoherence tells us why classicality emerges, but not why measurements have definite results. The question remains, what determines the actual event that we observe, and what happens to the alternatives? Several interpretations of quantum mechanics have been developed to address this issue, each offering a different answer to the measurement problem. The many-worlds interpretation, proposed by Hugh Everett in the 1950s, suggests that the wave function never collapses at all. Instead, every possible outcome of a quantum measurement actually occurs, each in a separate branch of a continuously splitting universe. In this view, the measurement problem is resolved by eliminating the need for collapse. Reality is not singular, but branching. Every time a measurement is made, the universe divides, and the observer becomes entangled with each possible result. This interpretation removes the need for a special measurement rule, but it introduces a radical revision of what reality is. It also raises questions about probability. If all outcomes occur, then what does it mean to assign probabilities to them? Another approach is the objective collapse theory, which postulates that wave function collapse is a real physical process that occurs randomly, independently of observers. One well-known version is the Gerardi-Rimini-Weber model, which introduces a small but non-zero chance that any particle's wave function will spontaneously collapse. These collapses are rare for individual particles, but they accumulate for larger systems, ensuring that macroscopic objects always appear definite. Objective collapse theories solve the measurement problem by modifying the Schrödinger equation itself. They make collapse part of the physics, not a mysterious external process. But so far, these theories lack direct experimental support, and they often introduce new constants and assumptions that complicate the theory. Still others turn to epistemic interpretations, like QBism, which we will explore in more depth later. These interpretations view the wave function not as a description of reality, but as a representation of the observer's personal beliefs or information about possible outcomes. In this view, collapse is not a physical event, but a change in knowledge. The measurement problem is not a problem of physics, but of interpretation. Across all these approaches, one theme remains constant. The measurement problem demands that we rethink the relationship between observer and observed, between possibility and actuality. Whether through branching universes, spontaneous collapse, or shifts in belief, each interpretation offers a different vision of what it means to measure and, by extension, what it means to be real. The persistence of the measurement problem also underscores a deeper issue in quantum theory, its inability to fully describe how the world we experience, of definite outcomes and tangible objects, emerges from a mathematical formalism that describes only probabilities and superpositions. Among the many interpretations proposed to resolve the paradoxes of quantum mechanics, few are as provocative or as controversial as the idea that consciousness itself causes the collapse of the wave function. According to this hypothesis, the process by which a quantum system transitions from a superposition of many possible states to a single, definite outcome is not merely physical. Instead, it requires the presence of a conscious observer. While this idea has often been treated as speculative or metaphysical, it has a serious pedigree. Its roots stretch back to the early thinkers of quantum theory, including John von Neumann and Eugene Wigner, whose work we have already encountered in previous sections. But what exactly does this hypothesis propose, and how did it emerge from the formal structure of quantum mechanics? To begin, let us recall the central issue. In the standard quantum framework, a system evolves in a superposition of possible states until a measurement is made. The mathematics of the Schrödinger equation predicts how this superposition changes over time, but it does not account for why one outcome is realized while others are not. The collapse of the wave function, the apparent jump from many possibilities to a single actuality, is not described by the theory. It is inserted as an extra postulate. John von Neumann, in his rigorous mathematical treatment of quantum mechanics published in the early 20th century, tackled this issue directly. He pointed out that if every part of a measurement chain is treated quantum mechanically, including the measuring device, the environment, and even the observer's brain, then the entire chain becomes entangled. There is no obvious place in this sequence where the wave function must collapse. Unless we posit a special process that interrupts the chain, quantum mechanics seems to predict that the observer too enters a superposition of possible experiences. But our experience is not like that. When we observe a quantum event, we see one outcome, not a blur of all possible outcomes. Von Neumann concluded that the chain must be broken at some point. He suggested that the conscious mind of the observer may be the only place where this break can logically occur. In his view, consciousness is not just a bystander in quantum events, it is the agent that actualizes one outcome from among many. Eugene Wigner took this idea even further. In his Wigner's friend thought experiment, which we explored in the previous section, he imagined a situation in which one observer, the friend, performs a quantum measurement, but is herself still described by a superposition from the point of view of a second observer, Wigner. Wigner argued that the collapse of the wave function only occurs when the second, external observer becomes consciously aware of the measurement outcome. For Wigner, this led to a startling conclusion. Consciousness is not merely involved in quantum measurement, it is essential to it. The act of becoming aware, in the subjective sense, is what resolves the indeterminacy of the quantum state. Without consciousness, the system remains in a limbo of possibilities. This line of thinking came to be known as the consciousness causes collapse hypothesis. It implies that the mental act of observation is not a passive reflection of physical reality, but an active participant in shaping it. The world becomes definite, not when it is measured by an instrument, but when it is experienced by a conscious mind. Needless to say, this idea has been met with skepticism. Many physicists have rejected it outright, arguing that it introduces unnecessary and untestable metaphysical elements into a physical theory. Critics point out that consciousness is poorly understood, and bringing it into the foundations of physics only adds confusion. In their view, the measurement problem should be resolved by better understanding of quantum systems and their interaction with the environment, not by invoking mental phenomena. Yet the consciousness causes collapse hypothesis has not been entirely banished from serious discussion. Some philosophers of physics and a few physicists have continued to explore its implications. One prominent advocate is Henry Stapp, a theoretical physicist who has spent much of his career investigating the intersection of quantum theory and consciousness. Drawing on the ideas of von Neumann and Wigner, Stapp has argued that quantum mechanics offers a natural framework for understanding the mind-matter relationship. In Stapp's formulation, consciousness plays a dynamic role in selecting outcomes among quantum possibilities. He suggests that the brain operates as a quantum system, constantly evolving in a superposition of neural states. Conscious awareness then chooses among these states, effectively collapsing the wave function and guiding behavior. This, he argues, may offer a way to reconcile subjective experience with the physical workings of the brain. Although Stapp's ideas remain speculative, they illustrate one of the more intriguing possibilities raised by quantum mechanics. If consciousness is involved in the collapse process, then it is not merely an emergent feature of brain activity, it is a fundamental aspect of the universe, perhaps on equal footing with space, time, and matter. Of course, this interpretation raises many further questions. If consciousness causes collapse, then whose consciousness? Is the effect limited to human observers, or does it include animals? Does it require self-awareness, language, memory? What about artificial intelligence? Could a machine with sufficient cognitive capacity trigger wave function collapse? And even more provocatively, if no conscious observer is present, does the universe remain in a superposition? Was the early universe indeterminate until the emergence of conscious life? These questions touch on the philosophical and sometimes theological territory. They challenge our understanding of time, causality, and the relationship between mind and world. Some critics argue that the consciousness causes collapse hypothesis violates physicalism, the view that everything that exists is ultimately physical. If consciousness is required to resolve physical states, then it cannot be entirely reduced to matter. This could mean that the mind has causal powers not accounted for by physical law, a claim that many scientists find deeply problematic. Others counter that consciousness may itself be a quantum phenomenon. We will explore this idea in more detail in a future section when we examine proposals such as the orchestrated objective reduction (OR) model developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. But for now, it is enough to note that if consciousness plays a role in quantum events, then perhaps quantum theory must be expanded to include consciousness as a basic element. Still, most physicists remain cautious. The majority view is that while the measurement problem is real, it should be resolved by understanding the interaction between quantum systems and their macroscopic environments, not by invoking the human mind. Decoherence, objective collapse theories, and epistemic interpretations all seek to preserve a physicalist account of quantum phenomena without needing to redefine the role of consciousness. Nevertheless, the consciousness causes collapse hypothesis continues to fascinate. It challenges our assumptions about the nature of mind, the limits of science, and the meaning of observation. Whether or not it proves to be correct, it serves an important role in the philosophical exploration of quantum mechanics. It forces us to ask what it really means to observe, to know, and to exist. If the idea that consciousness causes collapse seems too speculative or metaphysically burdensome, an entirely different solution to the quantum measurement problem stands ready with equal boldness, yet rooted firmly within the mathematics of quantum theory. This is the many worlds interpretation, a radical proposal that removes the collapse of the wave function altogether. Instead of selecting a single outcome from a range of quantum possibilities, it posits that every possible outcome actually occurs, each in its own separate and branching universe. The many worlds interpretation, or MWI for short, was first introduced in the mid-20th century by American physicist Hugh Everett III. At the time, Everett was a graduate student at Princeton University, working under the supervision of John Wheeler, a prominent physicist with a deep interest in the foundations of quantum theory. Everett's doctoral thesis, completed in the year 1957, proposed what he called the relative state formulation of quantum mechanics. Everett's core insight was simple but profound. The mathematical formalism of quantum theory works beautifully when applied to isolated systems, but things become murky when we insert a mysterious collapse during measurement. Why not? Everett asked. Just take the Schrödinger equation seriously for all systems, including the observer and the measuring apparatus. If the wave function never collapses, then the evolution of the universe remains smooth, deterministic, and governed entirely by the Schrödinger equation. No exceptions, no added rules. In this framework, when a measurement occurs, the observer becomes entangled with the system being observed. The combined system evolves into a superposition of all possible outcomes. Each outcome still exists, but now in a separate branch of reality. For example, if a physicist measures the spin of a quantum particle and there are two possible results, spin up and spin down, then both outcomes occur. But the physicist who observes spin up becomes separated from the version of herself who observes spin down. Each version exists in a different world, unaware of the other. The implication is extraordinary. The universe constantly splits into parallel versions of itself, each representing a different outcome of every quantum event. These worlds do not interfere with one another, and each contains its own version of the observer, convinced that only one outcome occurred. There is no need for collapse, and no need for a special role for consciousness. Everett's proposal was revolutionary, but it was not warmly received at the time. Many physicists found it difficult to accept the existence of countless parallel universes just to preserve the deterministic evolution of the wave function. Niels Bohr and his colleagues, who had shaped the Copenhagen interpretation, reportedly dismissed Everett's ideas as unnecessary and metaphysically extravagant. Even John Wheeler, Everett's advisor, eventually distanced himself from the theory. As a result, Everett's work fell into obscurity for several decades. He left academic physics shortly after completing his dissertation and pursued a career in defense analysis and mathematics. He passed away in the year 1982, never seeing the full impact of his ideas on the future of quantum theory. Yet beginning in the 1980s and accelerating in the 21st century, the many worlds interpretation experienced a dramatic resurgence. Physicists and philosophers began to re-examine Everett's proposal with fresh eyes, recognizing its elegance and consistency. It offered a way to resolve the measurement problem without introducing undefined processes or invoking the mystery of consciousness. In the many worlds view, the quantum formalism is complete as it stands. No extra assumptions are required. One of the leading modern advocates of MWI is physicist Bryce DeWitt, who helped popularize the term many worlds and clarified the implications of Everett's work. DeWitt emphasized that MWI is not an addition to quantum theory. It is quantum theory, taken literally. All that is needed is to accept the universal validity of the Schrödinger equation. Another influential proponent is David Deutsch, a theoretical physicist at the University of Oxford and a pioneer in the field of quantum computing. Deutsch argues that the success of quantum algorithms, which rely on the simultaneous existence of multiple computational states, lends empirical weight to the many worlds view. According to Deutsch, when a quantum computer performs a calculation, it does so by exploring all possible paths in parallel across multiple branches of reality. Still, the many worlds interpretation raises difficult questions. If all outcomes occur, then what does it mean to assign probabilities? In the Copenhagen interpretation, the square of the wave function gives the probability of observing a particular result. But in many worlds, all results happen. How then do we make sense of probability in a universe where nothing is left out? Everett addressed this issue by proposing that probabilities correspond to the measure or amplitude of each branch. The thicker or more robust the branch, the more likely an observer is to find herself within it. Subsequent work by decision theorists and philosophers, such as David Wallace and Simon Saunders, has attempted to show that rational agents within the many worlds framework can make sense of quantum probabilities as degrees of belief about their future selves. Though this approach is still debated, it aims to reconcile the subjective experience of uncertainty with an objectively branching universe. Another criticism of MWI concerns the apparent extravagance of postulating an uncountable number of unseen worlds. Critics argue that the theory violates Occam's razor, the principle that scientific explanations should not multiply entities beyond necessity. If collapse works and gives the right predictions, why complicate matters with an infinite multiverse? Supporters of MWI reply that the number of entities is not what matters. What matters is the simplicity and coherence of the laws. In their view, many worlds is conceptually cleaner than Copenhagen or consciousness-based interpretations because it does not require a break in the mathematical formalism or the introduction of poorly defined processes. The wave function evolves smoothly, and everything follows from that single rule. Yet the many worlds view carries philosophical and emotional consequences that can be unsettling. It suggests that with every decision we make, the universe splits into new versions of reality. Every possibility is actualized somewhere. In one world, a person accepts a job offer. In another, they do not. In one world, a scientist confirms a breakthrough discovery. In another, the data says otherwise. This infinite branching seems to rob decisions of their finality and outcomes of their uniqueness. Some find this vision exhilarating, a grand cosmic tapestry in which every path is explored. Others find it deeply alienating, even nihilistic. If every possible version of ourselves exists, what meaning does any particular version hold? From a scientific standpoint, one of the biggest challenges facing MWI is that it is empirically indistinguishable from other interpretations. Because all branches are non-interacting, we cannot observe or access other worlds. This makes MWI difficult, if not impossible, to test directly. Its supporters argue that empirical equivalence should not disqualify a theory if it offers greater explanatory power and consistency. But critics maintain that a theory that cannot be falsified should be treated with caution. Nevertheless, MWI continues to attract interest, especially in fields like quantum computing, cosmology, and the philosophy of physics. Its implications stretch far beyond quantum theory, touching on the nature of time, identity, and reality itself. By taking the mathematics of quantum mechanics at face value and removing the need for an observer-triggered collapse, it presents a compelling alternative to consciousness-based models. In doing so, it also reframes the role of the observer. In MWI, the observer is not a special entity whose awareness causes collapse. Instead, the observer is a quantum system like any other, subject to the same rules of evolution and entanglement. Observation is simply interaction, nothing more. The conscious experience of a single outcome arises because each version of the observer becomes decohered from the others, unable to perceive alternative branches. This stands in sharp contrast to interpretations that give consciousness a privileged status in the unfolding of physical events. It also raises the bar for any theory that does posit a role for consciousness. If quantum mechanics works without collapse and without observers, then any alternative must explain not only why collapse happens, but why the elegant, universal mathematics of many worlds should be broken in the first place. The quantum world is governed by a strange logic. Particles can exist in superpositions, entangled systems can span vast distances, and measurement seems to play a peculiar role in shaping what we observe. But as we move from the microscopic to the macroscopic world, the realm of chairs, planets, and people, quantum strangeness appears to fade away. Why don't we ever see a table in a superposition of two positions, or a cat that is both alive and dead? What mechanism explains this smooth transition from quantum possibility to classical reality? One of the most powerful and widely accepted explanations for this transition is the theory of decoherence. While it does not solve every mystery of quantum measurement, decoherence provides a natural physical account of how quantum systems lose their quantum character when they interact with the environment. It offers a bridge between the two worlds, one that may reduce or even eliminate the need for mysterious wave function collapses or the intervention of consciousness. The idea of decoherence began to take shape in the latter half of the 20th century, gaining traction through the work of several key physicists. Among the earliest to propose a mechanism for the emergence of classicality was German physicist H. Dieter Zeh. who published a foundational paper on the topic in the year 1970. They showed that when a quantum system interacts with its surrounding environment, its wave function becomes entangled with countless environmental degrees of freedom, effectively spreading the system's quantum information beyond reach. Soon after, the concept was further developed and formalized by physicists such as Wojciech Zurek, who played a leading role in demonstrating how decoherence could explain the apparent collapse of the wave function without invoking any new physics. Zurek's work illustrated that quantum interference, one of the defining features of superposition, becomes rapidly suppressed as a result of environmental entanglement. As a result, the system appears to behave classically, even though, in principle, its wave function still evolves according to the Schrödinger equation. To grasp decoherence intuitively, consider a simple quantum system, a particle in a superposition of two locations. As long as the system is perfectly isolated, its quantum state remains coherent. The superposition is intact. But in the real world, perfect isolation is nearly impossible. The particle interacts with air molecules, photons, and other particles. Each interaction entangles the system with parts of the environment, encoding information about its possible states into the surroundings. This process causes the off-diagonal terms of the system's density matrix, the mathematical terms responsible for interference, to diminish rapidly. In other words, the system loses its capacity to exhibit quantum interference. Although no true collapse occurs, the system behaves as if it had collapsed into a definite state. From the point of view of an observer, the outcome is indistinguishable from what one would expect if the wave function had collapsed. This is the power of decoherence. It explains why macroscopic objects do not exhibit observable superpositions. A dust particle, for instance, decoheres in a fraction of a second due to interactions with the air and light around it. A human observer, composed of trillions upon trillions of particles, decoheres even faster. By the time we become consciously aware of any measurement, all relevant quantum correlations have been lost to the environment. Importantly, decoherence does not involve any modification of the fundamental equations of quantum mechanics. There is no need to insert a special rule for measurement or collapse. Everything follows from the unitary deterministic evolution described by the Schrödinger equation. In this sense, decoherence is not an interpretation of quantum mechanics. It is a physical process that helps clarify how quantum probabilities become classical facts. But decoherence does not answer every question. It explains how interference disappears, but it does not explain why one particular outcome is experienced rather than another. From the perspective of the wave function, all possible outcomes are still present, just no longer able to interfere. The role of the observer remains unclear. Decoherence describes how a system becomes entangled with its environment, but it does not describe how an observer becomes aware of a specific result. In this regard, decoherence is often described as a pre-measurement mechanism. It sets the stage for the appearance of classical outcomes, but it does not pick which outcome becomes real. It reduces the need for collapse, but it does not eliminate the philosophical dilemma at the heart of quantum theory. Still, decoherence has found a natural synergy with certain interpretations of quantum mechanics. In the many-worlds interpretation, for instance, decoherence explains why the different branches of the wave function become isolated from each other. Once decoherence occurs, each branch evolves independently, with no possibility of interference. Each branch corresponds to a different world in which a particular outcome is realized. Decoherence thus provides the mechanism by which these worlds diverge. In objective collapse theories, decoherence works alongside spontaneous collapses. It ensures that only one outcome becomes stable and persistent, while the others fade due to collapse dynamics. In quantum Bayesian or epistemic interpretations, decoherence explains how observers update their knowledge about a system based on interactions with the environment. Decoherence also has practical applications beyond foundational questions. In quantum computing, for example, decoherence is a major challenge. Qubits, quantum bits, must be kept in coherent superpositions to perform computations. Any interaction with the environment causes decoherence and disrupts the computation. Developing error correction protocols and shielding systems from decoherence is one of the central engineering problems in building functional quantum computers. In quantum cryptography, decoherence is used to detect eavesdropping. If a third party interacts with a quantum communication channel, decoherence occurs, altering the state in a detectable way. This property underlies the security of quantum key distribution. Experimental evidence for decoherence is overwhelming. Physicists have demonstrated the gradual loss of coherence in a wide variety of systems, from simple particles to complex molecules. In one striking experiment, researchers sent large organic molecules, composed of hundreds of atoms, through a double-slit setup and observed interference. But as environmental interactions increased, the interference vanished, just as decoherence theory predicts. These experiments confirm that decoherence is a real, physical process, not just a theoretical construct. It happens quickly and universally, making it one of the most robust mechanisms in quantum theory. Yet, it remains a subtle phenomenon. The information lost to the environment is not destroyed. It is simply dispersed into so many degrees of freedom that it becomes practically unrecoverable. This distinction is important. Decoherence is not the same as dissipation. It does not mean that energy is lost, only that phase relationships, the correlations that define quantum interference, are no longer accessible. In principle, if one could track every environmental particle involved in decoherence, it might be possible to reverse the process. But in practice, this is unimaginably difficult, making decoherence effectively irreversible. By grounding the transition from quantum to classical in environmental interactions, decoherence offers a powerful explanatory framework. It demystifies why we do not see macroscopic superpositions, and it reduces the mystery surrounding the act of measurement. It allows physicists to retain the universal validity of quantum equations without appealing to non-physical elements. However, decoherence does not entirely eliminate the need for interpretation. It clarifies how classicality emerges, but not why one result is experienced instead of another. It remains compatible with multiple interpretations of quantum mechanics, each offering different views on the nature of probability, reality, and the observer. In this way, decoherence stands as a cornerstone of modern quantum theory, both as a physical process and as a conceptual tool. It brings quantum theory closer to everyday experience without requiring dramatic changes to its formalism, but it also leaves room for deeper questions about knowledge, belief, and the meaning of measurement. While many interpretations of quantum mechanics aim to describe what exists in the world, whether that be particles, wave functions, or branching universes, there is a growing school of thought that challenges this very premise. Instead of viewing quantum theory as a description of physical reality out there, quantum Bayesianism, or QBism, treats it as a user's manual, a tool for making sense of personal experience and guiding rational decision-making. In this framework, quantum probabilities are not objective features of the world, but subjective degrees of belief grounded in the agent's expectations. At the core of QBism is a shift in perspective. It does not ask, what is the system doing, but rather, what should I believe about the system's potential behavior? This approach takes inspiration from Bayesian probability theory, in which probabilities are interpreted not as physical tendencies or long-run frequencies, but as measures of an individual's degree of belief based on available information. The primary architects of QBism are physicists Christopher Fuchs and Rüdiger Schack, along with philosopher David Mermin. Their collaboration over the past 2 decades has led to a complete reimagining of what quantum mechanics means, not as a theory of the external world, but as a theory of how agents interact with the world and update their beliefs in response to experience. To understand the motivation behind QBism, it helps to recall the persistent confusion surrounding the quantum state, or wave function. In standard interpretations, the wave function is a mathematical object that evolves according to the Schrödinger equation and upon measurement appears to collapse into a definite outcome. But what is the wave function? Is it a real physical field, a description of an underlying reality, or simply a convenient tool? In the QBist view, the wave function is not a physical entity at all. It is a reflection of the agent's personal belief about the outcomes of potential experiments. When an agent assigns a wave function to a system, they are expressing their own expectations based on prior experience and current knowledge. There is no implication that the wave function exists independently of the agent. This subjective interpretation of the wave function has radical consequences. It implies that different observers may assign different wave functions to the same system, depending on their information and experiences. And that's entirely acceptable within QBism because quantum theory is not making claims about an objective state of affairs. It is providing a structured way for individuals to organize and revise their beliefs in light of new data. The use of Bayesian reasoning is central to this process. In classical Bayesian theory, an agent begins with a prior belief and updates that belief upon receiving new evidence. The probability assigned to an event reflects the agent's confidence, not an external property of the event. QBism extends this logic into the quantum realm. The Bohr rule, which in standard quantum mechanics gives the probability of measurement outcomes, is treated in QBism as a normative rule. It tells the agent how to maintain internal consistency among their beliefs about different experiments. One of QBism's most striking claims is that the outcomes of quantum measurements are personal experiences. When an agent performs a measurement, they are not discovering a pre-existing value. Rather, the measurement is an action taken by the agent, and the outcome is the agent's personal experience of the world's response. This is not to say that the world is entirely subjective or that anything goes. QBism still recognizes an external world that resists and surprises, but it emphasizes that science begins with experience, and quantum theory provides the best guide we have for navigating that experience rationally. In this way, QBism avoids many of the conceptual traps that plague other interpretations. It does not require wave function collapse, because the wave function is not a real object. It does not face the problem of multiple branches or parallel worlds, because measurement outcomes are not thought to coexist in a universal wave function. Nor does it require a special role for consciousness in collapsing possibilities, since there is no collapse to begin with. Instead, quantum mechanics becomes a deeply personal and participatory framework, grounded in the actions and expectations of individual agents. Critics of QBism often object that it seems to abandon the goal of physics to describe a shared, objective reality. If quantum mechanics is merely a guide for belief, how can it tell us anything about the world we all inhabit? And how can different observers coordinate their beliefs if each one constructs their own version of reality? The QBist response is subtle but powerful. First, QBism does not deny the existence of a shared world. What it denies is that quantum mechanics tells us about that world directly. Instead, it tells us how to navigate our experiences within it. The goal is not to describe reality in the abstract, but to provide each agent with a reliable framework for making decisions, predicting outcomes, and learning from experience. Second, the structure of quantum theory itself ensures that different agents can reach consistent conclusions. The rules of probability, the Bohr rule, and the symmetries of quantum formalism constrain what beliefs are rational. In this way, QBism provides a common grammar that allows individuals to communicate, coordinate, and build scientific consensus, even if their initial experiences and priors differ. One useful analogy is language. No single language perfectly describes the world, but language allows us to share our experiences and develop mutual understanding. Similarly, quantum mechanics, in the QBist view, is not a mirror of reality, but a tool, a highly structured language for interacting with the world and with each other. Another criticism of QBism is that it appears too anthropocentric, too focused on human agents. What about non-human observers, such as automated detectors, computers, or animals? QBism handles this by generalizing the concept of agent. An agent, in this context, is any system capable of making decisions, forming expectations, and updating beliefs. While human agents are the most familiar, the theory can be extended to other kinds of observers, as long as they meet these criteria. Moreover, QBism reframes the entire notion of measurement. Rather than being a special process that causes collapse, measurement is simply an interaction, an action taken by an agent that yields a response from the world. The agent interprets this response as an outcome and uses it to update their beliefs. This interpretation is highly operational. It focuses on what agents do, not on metaphysical speculation about what exists behind the scenes. Despite its unorthodox approach, QBism has attracted growing interest among physicists and philosophers of science. It offers a fresh and rigorous alternative to the standard narratives, while avoiding some of the paradoxes that have long haunted quantum foundations. Its emphasis on agency, belief, and experience resonates with broader philosophical traditions, including pragmatism and phenomenology. Yet QBism also leaves open important questions. What, if anything, can it tell us about the underlying nature of the world? Is there a deeper theory waiting to be discovered, one that connects subjective experience with objective structure? And how does QBism relate to other areas of physics, such as relativity or cosmology? These questions are still being explored, and QBists themselves do not claim to have all the answers. But they argue that the strength of their approach lies in its clarity and coherence. By treating quantum theory as a tool for making sense of experience, rather than a window into ultimate reality, QBism sidesteps many of the conceptual dead ends that have ensnared other interpretations. In doing so, it offers a new vision of science, not as the passive description of an external world, but as a participatory activity grounded in experience, judgment, and interaction. Science, in this view, is a personal journey through a shared and mysterious landscape. For much of the 20th century, debates about the foundations of quantum mechanics were often regarded as philosophical, stimulating, yes, but divorced from the practical business of doing physics. As long as the equations delivered accurate predictions and technology kept advancing, many physicists felt content to set aside the deeper interpretive questions. But that began to change in the latter half of the century and accelerated dramatically in the early years of the 21st. What once seemed like metaphysical speculation has become the subject of precise, cutting-edge experiments, some of which have tested the limits of reality itself. One of the most significant developments in this domain is the emergence of loophole-free Bell tests, a set of experiments designed to probe the foundational questions raised by John Bell's theorem, which we explored in a previous section. These tests address the heart of the conflict between quantum mechanics and the classical worldview, and they do so not through abstract theory, but through the cold precision of the laboratory. To briefly recall the context, Bell's theorem demonstrated that no theory of local hidden variables can reproduce all the predictions of quantum mechanics. That is, if particles have pre-existing properties and no influence can travel faster than light, then certain statistical correlations should never occur. Yet quantum mechanics predicts, and experiments have confirmed, that those very correlations do occur when entangled particles are measured in specific ways. But for decades, every experimental attempt to test Bell's inequalities faced loopholes, possible alternative explanations that could account for the results without requiring the abandonment of locality or realism. These loopholes did not disprove the quantum predictions, but they left a narrow escape route for classical interpretations. One of the earliest and most famous sets of experiments was conducted by Alain Aspect and his team at the Institut d'Optique in France in the early 1980s. These experiments used entangled photons and variable measurement settings to test Bell inequalities, and the results showed violations consistent with quantum theory. However, they were not fully conclusive because of two primary issues: the locality loophole and the detection loophole. The locality loophole refers to the possibility that the two measuring devices might somehow influence each other, either directly or indirectly, perhaps through unknown or subliminal channels. If such communication occurs, the assumption of locality is violated not by nature, but by the design of the experiment. To close this loophole, the measurement settings must be chosen and changed so quickly and so independently that no signal traveling at or below the speed of light could link the two detectors before the measurements are completed. The detection loophole involves the fact that not all entangled particles are detected in typical experiments. If the particles that are detected form a biased subset, then the observed correlations might not reflect the full set of events. This opens the door to so-called fair sampling assumptions, which state that the detected subset is representative. But without closing this loophole, skeptics can argue that the data might reflect selection effects, not fundamental quantum behavior. For many years, no single experiment succeeded in closing both loopholes simultaneously. Some experiments focused on closing the locality loophole by separating detectors by large distances and using rapid random number generators to choose measurement settings. Others focused on closing the detection loophole by improving detector efficiency, especially in experiments with ions or other massive particles. But until recently, no experiment closed all significant loopholes in one comprehensive setup. That changed in the second decade of the 21st century, when several independent research teams succeeded in performing loophole-free Bell tests, experiments that simultaneously closed both the locality and detection loopholes under rigorous conditions. One of the most notable was conducted by a team led by physicist Ronald Hansen at Delft University of Technology in the Netherlands. Their experiment, reported in the year 2015, involved pairs of entangled electrons trapped in diamond defects at two separate laboratories more than 1 kilometer apart. The measurement settings were chosen independently at each site using fast random number generators, and the results were recorded within a time window too narrow for any signal to travel between the labs, even at the speed of light. The results of the Hansen experiment showed a clear violation of Bell's inequality, consistent with quantum predictions and incompatible with any local hidden variable theory. Because of its design, the experiment successfully closed both the locality and detection loopholes. It was, in the words of many physicists, a milestone, the first fully loophole-free test of Bell's theorem using massive particles and state-of-the-art quantum control. Around the same time, other teams performed similar experiments using entangled photons and different experimental configurations. Researchers at the National Institute of Standards and Technology, NIST, in the United States and the Institute for Quantum Optics and Quantum Information, IQOQI, in Vienna, each published independent results confirming the violation of Bell inequalities without relying on the assumptions that had plagued earlier tests. The cumulative effect of these experiments has been to dramatically strengthen the empirical case for quantum non-locality. The implications are staggering. The universe, as described by quantum mechanics, does not obey the intuitive rules of local realism. Either objects do not possess definite properties until measured, or influences can propagate instantaneously across space, or perhaps some third possibility that we have yet to comprehend. These experiments have not, however, resolved the question of interpretation. Quantum mechanics continues to offer multiple competing frameworks for understanding these results. The Copenhagen interpretation, the many worlds interpretation, objective collapse theories, QBism, and others all offer ways to accommodate non-local correlations, but they differ radically in their ontological commitments. What the loophole-free Bell tests have done is constrain the possible interpretations. They rule out large classes of local hidden variable theories and force any remaining classical explanations to become increasingly contrived and implausible. The experimental evidence is not merely consistent with quantum mechanics, it is decisive in its favor over classical alternatives. Beyond foundational philosophy, these results have practical applications. Quantum entanglement, once a curious oddity, is now a central resource in technologies such as quantum cryptography, quantum computing, and quantum teleportation. The same principles that violate Bell's inequalities can be harnessed to create secure communication channels, perform computations that outpace classical computers, and transmit quantum states across long distances. For example, quantum key distribution protocols like BB84 and E91 use entangled particles to guarantee security. Any attempt to eavesdrop introduces disturbances that are immediately detectable. These technologies rely on the very same quantum correlations tested in Bell experiments, showing that what once seemed philosophically exotic is now technologically indispensable. Moreover, future experiments continue to push boundaries. Researchers are working on cosmic Bell tests, in which the choices of measurement settings are determined by photons emitted from distant stars or quasars. The idea is to push the separation between the events far enough in space and time that any hidden variables would have to originate billions of years ago, eliminating even more speculative loopholes. These cosmic experiments are designed to test the principle of freedom of choice, the assumption that the experimenter's decisions are not correlated with hidden variables that determine the outcomes. By using astronomical sources that have not interacted with Earth since long before the solar system formed, physicists aim to place even stricter bounds on classical explanations. As these tests become increasingly sophisticated, the philosophical implications grow deeper. What do we make of a universe in which measurement outcomes are correlated across vast distances in ways that cannot be explained by shared local causes? What does it mean for reality that entangled particles behave as a single system, even when separated by kilometers or light years? While these questions remain open, the empirical progress is undeniable. Where once the quantum revolution rested on strange mathematics and unresolved paradoxes, it now rests on a firm bedrock of experimental data. The laboratory has become a window into the most fundamental workings of the universe. The measurement problem in quantum mechanics and the mystery of consciousness in neuroscience are, at first glance, entirely distinct domains. One grapples with the unpredictable outcomes of quantum measurements. The other seeks to understand how subjective experience arises from physical processes in the brain. Yet, as researchers have delved deeper into the foundations of both fields, an audacious question has emerged. Could consciousness itself be a quantum phenomenon? Could the peculiarities of quantum mechanics help explain the most intimate and mysterious aspect of human existence, the conscious mind? This question sits at the intersection of physics, biology, and philosophy. Though speculative, it is not without its scientific motivations. For decades, consciousness has remained a stubborn enigma. Neuroscientists have mapped countless neural circuits, uncovered the biochemistry of synaptic transmission, and identified brain regions associated with perception, emotion, memory, and decision-making. But none of this has fully explained the hard problem of consciousness. How and why does the activity of neurons give rise to the experience of being? From one perspective, this may seem like a problem of complexity. Perhaps consciousness simply emerges from the right arrangement of physical processes, much like liquidity emerges from the interactions of water molecules. But others argue that this approach, rooted in classical physics, misses something essential. They suggest that consciousness might not emerge from classical interactions alone, but rather depend on quantum-level dynamics that introduce non-classical properties such as superposition, entanglement, and non-locality. One of the earliest proponents of this idea was physicist Roger Penrose, who in the latter half of the 20th century began arguing that classical computation could not fully account for human consciousness. In his view, mathematical insight, creativity, and the perception of meaning involve something more than mechanical symbol manipulation. He proposed that consciousness might involve non-computable processes, those that could not be simulated by a Turing machine. This led Penrose to explore the possibility that the brain might operate at the quantum level, and that consciousness could arise from quantum state reduction or collapse. According to Penrose, standard interpretations of quantum mechanics, which treat collapse as a probabilistic event, miss something crucial. He hypothesized instead that wavefunction collapse is an objective physical process triggered by gravity. In this view, there is a threshold beyond which a quantum superposition becomes unstable under the influence of space-time curvature, causing it to reduce to a single outcome. To develop this idea into a concrete theory of consciousness, Penrose partnered with anesthesiologist Stuart Hameroff, who brought insights from cellular biology and neuroscience. Together, they proposed the orchestrated objective reduction, OR theory. This model suggests that quantum computations take place in structures called microtubules, protein-based components of the cell's cytoskeleton, abundant in neurons. Microtubules, according to Hameroff and Penrose, could act as quantum processors. Within them, quantum states could become entangled and evolve coherently before collapsing in a way that correlates with conscious experience. The orchestration in OR refers to biological mechanisms that synchronize and regulate these quantum processes. In this framework, consciousness is not simply brain activity, it is quantum computation followed by objective wavefunction reduction. This proposal was, and remains, highly controversial. Critics argue that the warm, wet, and noisy environment of the brain is incompatible with quantum coherence. In standard physics, quantum states are extremely fragile. They decohere rapidly when exposed to thermal fluctuations or environmental interference. Maintaining coherent quantum states in a biological system for any appreciable duration is considered, by many, to be practically impossible. However, some experimental evidence has emerged to challenge this assumption. In recent decades, researchers have found evidence of quantum coherence in biological systems, most notably in photosynthesis. Studies on certain types of algae and bacteria have shown that energy transfer within light harvesting complexes may exploit quantum coherence to maximize efficiency. Similarly, in the navigation systems of migratory birds, there are hypotheses suggesting that quantum entanglement may play a role in magnetic sensing. These findings do not prove the Bohr theory, but they weaken the objection that biology and quantum mechanics cannot mix. If quantum effects can play a functional role in plant cells and avian brains, perhaps they are not entirely absent from human cognition. Still, the evidence remains circumstantial. No definitive experimental support for Bohr has yet been found. The theory makes bold claims, but measuring quantum coherence within microtubules remains a monumental technical challenge. Researchers continue to debate whether microtubules could indeed support quantum computation and whether the timescales and energies involved are compatible with known neural processes. Even so, the broader question remains compelling. Might quantum theory offer insights into the structure of consciousness, even if not its precise mechanism? Some thinkers have suggested that entanglement, for instance, may provide a physical basis for the unity of conscious experience. In classical systems, different parts can operate independently, but in entangled systems, the whole cannot be decomposed into independent parts without losing essential correlations. Could this property help explain why our thoughts, perceptions, and emotions feel like part of a single stream of awareness rather than disjointed events? Others have explored whether quantum indeterminacy might allow for genuine free will, a question that has long troubled both philosophy and neuroscience. In classical physics, every event is determined by prior conditions, but in quantum mechanics, outcomes are probabilistic. Some researchers speculate that conscious agents might influence quantum probabilities in ways that shape decisions and actions, though this idea is deeply contentious and lacks empirical support. More recently, researchers have begun to explore quantum cognition, a field that applies the mathematics of quantum theory to model human decision-making, perception, and memory. This approach does not assume that the brain is a quantum system in a physical sense, but rather that human thought sometimes follows quantum-like logic. For example, human decisions often violate the classical laws of probability, but they can be modeled more accurately using quantum probability theory. In this context, quantum does not refer to particles or superpositions, but to the structure of belief and inference. These efforts suggest that quantum theory may offer conceptual tools for understanding the mind, even if consciousness does not depend on quantum physics in a literal, mechanistic way. The abstract structures of quantum theory, contextuality, superposition, interference, may find parallels in cognitive processes, not because of physical similarity, but because of analogous dynamics. Still, the question of whether consciousness requires quantum mechanics remains open. There is, as yet, no consensus. Some neuroscientists continue to argue that classical models are sufficient to explain conscious experience. They point to the progress made in understanding neural networks, information processing, and global workspace dynamics. Others, however, believe that something fundamental is missing from these accounts, something that only a new kind of physics, perhaps rooted in quantum foundations, can supply. The debate remains active, not only in scientific circles, but also in philosophical ones. Does consciousness emerge from complexity alone, or does it reflect an underlying feature of the quantum universe? Are we observers of reality, or participants in its unfolding, perhaps even co-creators of its outcomes? As we have seen, the suggestion that consciousness plays a role in quantum mechanics, particularly in the collapse of the wave function, has intrigued scientists and philosophers for nearly a century. From the speculations of von Neumann and Wigner to the more recent theories involving quantum processes in the brain, this idea has never fully disappeared from the discourse. Yet despite its persistence, the consciousness causes collapse hypothesis remains highly controversial and is rejected by the vast majority of working physicists today. In this section, we examine the major criticisms leveled against consciousness-based interpretations. These critiques are not merely philosophical, they are grounded in scientific methodology, empirical reasoning, and a commitment to parsimony in theoretical frameworks. Understanding these objections is essential for evaluating where the current consensus lies in modern physics. Perhaps the most immediate and frequently voiced criticism is that consciousness is not a well-defined concept in physical terms. While neuroscience has made great strides in mapping brain activity and identifying correlates of conscious experience, there is still no agreed-upon scientific definition of what consciousness is, how it arises, or how to measure it. Introducing consciousness into quantum mechanics, therefore, is seen by many as introducing an undefined variable into a theory that otherwise functions with precise mathematical clarity. Physicist Sean Carroll has been among the most vocal critics of this approach. In his view, positing that consciousness causes wave-function collapse is not just speculative, it is a step backward in scientific reasoning. Carroll argues that we should not invoke poorly understood or metaphysically loaded concepts to explain phenomena that can be accounted for by better understood mechanisms, such as decoherence. As he puts it, we have no evidence that the brain or consciousness is doing anything that requires quantum mechanics to explain. Another major objection is that consciousness-based collapse theories lack predictive power. A good scientific theory not only explains known phenomena, but also makes testable predictions. The problem with saying that consciousness causes collapse is that it does not offer any measurable or falsifiable criteria. At what threshold does consciousness cause collapse? Does a frog observing a quantum system count? What about an artificial intelligence? If the presence or absence of consciousness cannot be tested in a controlled experiment, then the theory drifts into the realm of unfalsifiability, which is antithetical to the empirical nature of physics. Additionally, critics argue that such interpretations blur the boundary between physics and metaphysics. Physics, as a discipline, aims to describe the behavior of physical systems using mathematical models grounded in observation and experiment. Consciousness, by contrast, remains a largely subjective phenomenon, and incorporating it into the core of physical theory opens the door to idealism, the philosophical view that reality is fundamentally mental rather than material. While idealism has its own intellectual tradition, most physicists prefer to maintain a clear separation between subjective experience and objective measurement. Max Tegmark, another leading figure in the interpretation of quantum mechanics, has offered a more quantitative critique. In his research on the feasibility of quantum effects in the brain, Tegmark analyzed how long quantum coherence could realistically be sustained in neural environments. His conclusion was that quantum states would decohere extremely quickly, on the order of femtoseconds, in the warm, wet, and noisy conditions of biological tissue. In other words, the brain is far too chaotic an environment for quantum superpositions to persist long enough to have any functional relevance for consciousness. Tegmark's work deals a significant blow to models like OR, which rely on long-lived quantum coherence within neural microstructures. If such coherence cannot be sustained, then the underlying mechanism of these theories collapses, ironically, under the weight of environmental interaction. This bolsters the mainstream view that classical neural processes are sufficient to explain conscious experience, or at least are the best place to begin such explanations. Furthermore, many critics point to the lack of necessity in invoking consciousness. Quantum mechanics, despite its conceptual difficulties, functions extremely well without it. Every successful experiment, every verified prediction, and every technological application, from lasers to transistors to MRI machines, uses quantum theory without requiring a conscious observer to collapse the wave function. The physical interactions between systems, along with decoherence, provide a consistent framework that matches empirical data. In this light, bringing in consciousness appears not only unnecessary but unmotivated. The principle of Occam's razor, which holds that the simplest explanation with the fewest assumptions is usually best, suggests that we should avoid introducing complex concepts like consciousness unless there is no other alternative. And so far, there has been no empirical result that compels physicists to take consciousness-based interpretations seriously. Some argue that these interpretations also suffer from a kind of cognitive anthropocentrism, the idea that human consciousness must be central to how the universe functions. But as science has repeatedly shown, human beings are not at the center of the cosmos. The Earth is not the center of the solar system is not the center of the galaxy, and the galaxy is not the center of the universe. Why then should human consciousness be the final arbiter of quantum events? This line of reasoning leads many physicists to favor interpretations that minimize the role of the observer, such as the many worlds interpretation, objective collapse models, or decoherence-based accounts. These frameworks may still contain unresolved questions, but they do not require that mental states play a foundational role in determining physical reality. There is also a deeper concern that introducing consciousness into quantum theory might halt progress by diverting attention away from testable questions. If physicists begin to treat wave function collapse as a matter of subjective experience rather than physical interaction, they may lose sight of more productive avenues of investigation. As the physicist Asher Perez famously said, quantum phenomena do not occur in a Hilbert space, they occur in a laboratory. To be fair, even many critics acknowledge that consciousness remains a deep and unresolved mystery. They do not deny its importance, nor do they claim that current neuroscience explains it completely, but they argue that quantum physics is not the place to begin solving that mystery. Not because the two fields are incompatible, but because there is no clear evidence of a connection. It is worth noting, however, that criticism of consciousness-based interpretations does not mean closure on the matter. Science remains open to revision in light of new evidence. If, someday, experiments reveal measurable quantum effects in neural tissue, or if deviations from standard quantum predictions are observed in the presence of conscious agents, then the conversation would change dramatically. But until such evidence appears, most researchers regard the consciousness causes collapse hypothesis as an interesting but scientifically unsupported idea. The strength of quantum theory lies in its mathematical precision, its predictive accuracy, and its empirical success. Interpretations that retain those virtues while avoiding speculative additions tend to be favored. This is not to say that physicists lack curiosity or imagination, but that the bar for including new concepts into foundational physics is, and must be, very high. Quantum mechanics is not merely a set of mathematical rules used to predict the outcomes of experiments. It is a theory that cuts deeply into our most basic assumptions about reality. Over the last century, it has overturned long-held beliefs about determinism, locality, and the nature of physical properties. And regardless of which interpretation one favors, whether many worlds, decoherence, QBism, or something else, quantum mechanics challenges the very notion of an objective, observer-independent world. This section explores the broader philosophical and metaphysical consequences of quantum theory. While previous sections have focused on scientific frameworks and experimental data, here we step into the realm of fundamental concepts, those that underpin not only physics but also our understanding of what it means to exist, to observe, and to know. One of the most profound shifts introduced by quantum mechanics is the replacement of determinism with probabilism. Classical physics, as formulated by Newton and refined by Laplace, depicted a clockwork universe. Given complete knowledge of a system's initial conditions, the future could be predicted with absolute certainty. In such a universe, the future was already embedded in the present, awaiting only the work of calculation. Quantum mechanics shattered that vision. Even with complete knowledge of a system's wave function, the best we can do is assign probabilities to the outcomes of measurements. No amount of calculation can reveal which particular outcome will occur. The results are inherently indeterministic. This indeterminism is not due to ignorance, as it is in classical statistical mechanics. It is a fundamental feature of the theory, and this leads to philosophical questions. Is the universe intrinsically open-ended? Does the future truly exist in a plurality of possibilities? Or is the wave function merely a reflection of our ignorance, pointing back towards some hidden deterministic layer beneath the surface? These are not idle questions. If reality is fundamentally probabilistic, then the notion of cause and effect becomes more complex. Events no longer follow inevitably from prior events, but emerge from a web of probabilities. This undermines traditional notions of causal necessity, a cornerstone of both science and philosophy since antiquity. Equally unsettling is the phenomenon of non-locality, revealed through entanglement and confirmed by the violation of Bell's inequalities. In classical physics, objects are located in space and can only influence one another through local interactions, forces that travel through space over time. But quantum entanglement links particles in such a way that a measurement performed on one immediately affects the description of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, defies classical intuition. Although it cannot be used to transmit information faster than light, thus preserving the tenets of special relativity, it suggests that the quantum world is more deeply connected than our everyday experience allows. The universe, at its most fundamental level, may not be made of separate parts, but of relational properties that do not respect the boundaries of space and time in the way we once believed. This leads to the idea of relationalism, the view that properties are not intrinsic to objects, but arise through their interactions with other systems. In such a framework, the idea of a particle having a definite position or spin before measurement becomes meaningless. Instead, those properties exist only in relation to the measuring apparatus or the observer. Some interpretations, such as the relational interpretation proposed by Carlo Rovelli, embrace this idea fully. They propose that quantum mechanics does not describe an objective reality, but a network of relations between observers and systems. This raises deeper ontological questions. What is reality, if not a collection of observer-independent facts? Is reality a mosaic of relations, a field of potentialities, or an unfolding web of experiences? Does it make sense to speak of the world as it is, apart from what can be observed or measured? The consequences of this shift in perspective have been explored by philosophers such as David Chalmers, who is best known for his work on consciousness, and Thomas Nagel, who has written extensively on the tension between subjective experience and objective description. In their writings, the quantum framework is often cited as evidence that our current metaphysical models are incomplete. Nagel, for instance, has argued that science must eventually integrate first-person perspective into its worldview, and quantum mechanics, with its emphasis on observation, may point the way. The question of whether the observer is essential to the structure of reality is also a recurring theme. Some interpretations, like QBism, embrace this explicitly, treating quantum mechanics as a tool for agents to organize their experiences. In QBism, the quantum world is not out there waiting to be discovered, but is brought forth through the agent's interaction with it. This makes reality participatory, not passive. This participatory view finds echoes in the work of John Wheeler, who proposed the idea of it from bit. Wheeler suggested that information, bits, might be the most fundamental ingredient of the universe. According to this view, reality emerges from acts of observation, with each act adding a new bit of information to the cosmic ledger. This flips the traditional view of science on its head. Rather than the observer uncovering a fixed world, the observer plays an active role in shaping what is real. Such ideas bear a resemblance to older philosophical positions like idealism, in which reality is fundamentally mental, or phenomenology, which emphasizes the role of experience in constituting the world. Though modern physicists may shy away from these associations, the parallels are difficult to ignore. Even interpretations that try to maintain a classical realism, such as the many worlds interpretation, end up confronting their own metaphysical challenges. If every quantum event spawns a branching of the universe, then the cosmos becomes an ever-growing multiverse of unimaginable complexity. This may preserve determinism and objectivity, but at the cost of inflating reality to a size that defies comprehension. In this view, the observer is just one among an infinite number of selves, each experiencing a different path through a sprawling quantum landscape. All of these possibilities, indeterminism, non-locality, relationalism, participation, and the multiverse, suggest that quantum mechanics is not just a scientific theory, but a philosophical turning point. It invites us to rethink the assumptions that have guided science since the Enlightenment. No longer can we assume a detached mechanical universe governed by hidden variables and deterministic laws. Instead, we are faced with a world that is probabilistic, relational, and participatory. This has profound consequences for other areas of thought as well. In ethics, for example, a participatory universe may lend weight to the idea that our actions are not merely the unfolding of mechanical causality, but contribute to the formation of reality itself. In epistemology, the role of the observer invites a re-examination of what it means to know something. And in ontology, the study of what exists, quantum mechanics pushes us to consider whether existence itself may be contextual or dependent on interaction. Despite all this, it is important to remain grounded. While quantum mechanics challenges our intuitions and offers fertile ground for philosophical speculation, it remains first and foremost a scientific theory, a tool for making predictions and understanding the world. The philosophical implications are real, but they must always be weighed against empirical evidence, mathematical coherence, and theoretical clarity. As we arrive at the end of our journey through one of the most profound scientific questions of the modern age, does consciousness influence quantum mechanics? We find ourselves not at a final answer, but at a crossroads. Quantum theory remains among the most successful and precisely tested frameworks in all of science. It powers the technologies of the digital age, explains the structure of atoms, predicts the behavior of semiconductors, and lies at the heart of emerging fields such as quantum computing and quantum cryptography. Yet, despite this success, its deepest meaning remains open to interpretation. In this final section, we step back to ask, what have we learned, and where is the frontier now? Over the past century, quantum mechanics has revealed a universe that is startlingly different from the one imagined by classical physics. It is a universe where outcomes are probabilistic, where particles exist in superpositions, and where entangled systems defy classical separability. The theory's predictions have been confirmed time and again, with extraordinary precision, and yet, the question of what the theory means, especially concerning observation and consciousness, remains elusive. One of the clearest lessons from our exploration is that measurement plays a special role in quantum mechanics, but it is not yet fully understood. The theory accurately predicts the probabilities of different outcomes, but it does not specify why only one outcome becomes actual. Whether this collapse is real, apparent, or altogether unnecessary depends on the interpretation one adopts. The Copenhagen interpretation holds that properties become definite only upon measurement. Many worlds asserts that all outcomes occur, and we merely experience one branch. Decoherence explains how classical behavior emerges through environmental entanglement. QBism reimagines the wavefunction as an agent's personal belief. Objective collapse theories suggest that reduction is a physical process, while consciousness-based models posit that awareness plays a causal role. Each of these approaches resolves some questions while raising others. None is free from philosophical or empirical challenges. The debate continues not because of a lack of intelligence or effort, but because quantum mechanics, at its heart, is a theory that stretches the limits of what science can describe without venturing into metaphysics. So where does consciousness stand in this picture? We have seen that some physicists, beginning with von Neumann and Wigner, took seriously the idea that conscious observation might play a causal role in collapsing the wave function. Later proposals, such as OR, went further, suggesting that consciousness itself is a quantum process, rooted in coherent phenomena within neural microstructures, and we explored whether features of quantum theory, such as entanglement or indeterminacy, might provide clues to the unity and subjectivity of conscious experience. Yet, no decisive evidence has emerged to support the idea that consciousness causes collapse. No experiment has yet shown that a conscious observer is necessary to resolve quantum uncertainty. The standard account, where measurement outcomes are determined by physical interactions and decoherence, remains dominant among working physicists. Moreover, many in the scientific community are cautious of interpretations that lean heavily on consciousness, not because they reject the importance of the mind, but because consciousness itself is poorly understood. Until we can clearly define and quantify what consciousness is, and until we can experimentally test its involvement in quantum processes, any theory that invokes it remains speculative. Nevertheless, speculation has its place in science, especially at the edges of current understanding. The question of consciousness remains one of the greatest unsolved problems in both philosophy and neuroscience. If consciousness turns out to be non-reducible to classical neural processes, or if it exhibits features incompatible with classical physics, then quantum theory may yet play a role in explaining it. But speculation must be matched by rigor. As physicist David Deutsch once noted, the best theories are the ones that are both radical and testable. That is the challenge for future work on the quantum-mind connection. It is not enough to construct a compelling narrative or propose a fascinating model. The theory must generate testable predictions that distinguish it from other interpretations. This leads to one of the most exciting frontiers in modern physics, the search for experimental signatures of quantum foundations. Technologies are rapidly advancing to a point where questions once considered philosophical can now be tested in the lab. Loophole-free Bell tests, quantum interferometry with increasingly massive particles, delayed choice experiments, quantum teleportation, and cosmic Bell tests are just a few examples of how physicists are probing the boundary between quantum and classical realms. In the coming decades, it may be possible to design experiments that directly compare interpretations. For instance, objective collapse models predict tiny but measurable deviations from the standard quantum formalism. Ultra-sensitive detectors may soon be able to verify or refute such deviations. Similarly, quantum gravity proposals may offer new insights into whether the wave function collapse is tied to space-time structure. On the neuroscience front, research into the brain's quantum properties continues, albeit with caution. While most evidence to date supports classical explanations for neural activity, the field remains open to new findings. If long-lived quantum coherence is ever detected in biological systems, it would open the door to a new understanding of mind and matter. There is also a growing interdisciplinary effort to integrate ideas from quantum theory, information theory, and consciousness studies. Concepts such as quantum information, entropy, and the holographic principle are being applied in novel ways to questions about cognition, memory, and awareness. While much of this work is still speculative, it reflects a genuine attempt to connect the dots between distinct but deeply related mysteries. Beyond the technical and experimental challenges lies the philosophical and human dimension. Quantum mechanics forces us to confront the limits of knowledge. It reminds us that the act of observation is not passive but participatory, that reality may not exist in a fully defined state until it is interacted with. Whether or not consciousness plays a physical role, quantum mechanics teaches us that the observer matters, not as a metaphysical entity, but as a point of interaction where potential becomes actual. This insight resonates beyond physics. It touches on how we understand ourselves in relation to the world. Are we detached spectators in a deterministic cosmos, or are we participants in a dynamic and evolving reality? Are our choices merely outcomes of physical laws, or do they play a role, however small, in shaping the world we inhabit? As science progresses, these questions will continue to evolve. The relationship between consciousness and quantum mechanics may ultimately prove to be indirect or metaphorical, or it may turn out to be fundamental. We do not yet know, but the search for answers continues, not only in laboratories and equations, but in the curiosity that drives us to ask these questions in the first place. In conclusion, we can say this: quantum mechanics has forever changed the way we think about reality. It has taught us that uncertainty is not ignorance, that probability is not just a statistical convenience, and that observation is more than passive recording. Whether consciousness influences quantum mechanics or simply reflects it, the dialogue between mind and matter remains one of the most fertile and fascinating frontiers of human thought. The journey is far from over, but perhaps that is exactly the point. In a quantum universe, the end of one path is always the beginning of another.